Okay, we're now recording. Woohoo! All right, let me go over to the slides. I'm James. I think I've met everybody now, except you.
Nathan Iring.
Nathan, nice to meet you.
How are you?
And what are you studying?
So just finished MBA, waiting a year to apply for organizational behavior.
Cool. All right. That'll work. You pass. Just sense for everything else, for everybody else, we have people from all over. Most of you have met everybody, sort of, as I've been asking you names. And oh, I don't know you. You snuck in. I'm James.
I'm Marie.
Marie,
yes.
Marie, from where?
From South Carolina.
Oh, okay. Clemson. All right. Clemson's a good place. What are you studying out there? Or are you faculty out there? Sorry.
Bachelor is my. Well,
you know Jason?
Yeah. I'm finishing my dissertation. That's why I'm here.
Okay.
To do this stuff.
Great. Jason's a good guy.
And he's my chair.
Oh, okay. Lucky you.
Hopefully I'll have this done by the time I leave here, so there's a lot on here.
That would be awesome. I'll sit with you one-on-one if you need something. Okay. Any administrative stuff before we get started? Okay, I'm recording this. It will be available within 24 hours of us finishing. This is a boot camp. This is I don't know which, this is like 8th or 9th boot camp I've done. 6th here at BYU or 7th at BYU. And it is the hardest thing I do all year, easily. And I have 4 daughters, so that's saying something. I mean, this is hard. So I appreciate your patience. Before we get started, I thought I'd get to the important stuff. Best places to eat around here. Sorry, remote folks. This isn't really for you. But the Cannon Center, it's the big buffet. I'll take you there at lunch if you want to go. Then there's the Creamery on 9th for ice cream. It's like the best non-gelato in the world. And their kid scoop is like a single, and their double is like a quart. It's really good. Local BYU folks, you know what I'm talking about. It's good stuff. La Jolla Groves, if you're looking for a fancy place that's not like too fancy and not too expensive, La Jolla Groves is awesome. Good food. Pita Pit sounds awful. It's awesome, and it's walking distance. It's just down the road by the big intersection right before you got here, by the bowling alley and the Panda Express and the CBS. Indian food, Bombay House, fabulous. Get the chicken tikka masala. It's to die for. And then the Thai house cuisine is fabulous. Anyway, so that's important stuff. I removed? How did I miss that? Also this. Let me hide this. Things to do around here. I just put this slide in here for those of you who want to do something else aside from work while you're here. Really, really good stuff. Thanksgiving Point, if you have a car. Bean Museum is a wildlife museum, pretty cool. It's free. There are theaters galore. I'm actually going to see Sense and Sensibility on Saturday at the Hale Center Theater. A couple weeks ago, I saw Hamilton up the Eccles Theater and Riverdance, which was awesome. There's some good theater around here. There's Temple Square, which is gorgeous. Also the Provo City Center Temple, beautiful. Lots of hiking, waterfalls everywhere. Feel free to hike. If you don't know where to go, ask one of the locals. Ice cream, I talked about. Lots of cool geological stuff. Bryce Canyon is gorgeous if you want to spend 6 hours driving, but it's beautiful. Shopping at Sundance. Nightlife, there isn't a nightlife in Provo. I'm sorry. So no nightlife in Provo unless you like comedy, sports, things like non-alcoholic comedy clubs. But if you want some nightlife, go up to Sundance or Salt Lake. There's some good stuff. Okay. Just so I know who I'm dealing with. I know most of you, actually. I know about half of you pretty well. But are there any faculty here? Faculty.
What is faculty?
Professor. All right. Okay. And then generally, if you had to like rate yourself as a super savvy statistician to a super noob, like don't know anything about stats, where would you put your hand? Okay. That helps. Thank you. That really helps. You can't put it down. That wasn't an option. All right. But that helps me, so I know how fast, how slow to go. So we'll go accordingly. Same thing with SEM in particular. Looking good. About the same feeling. Okay. And then PLS. Really? Oh, that's good. Someone was like, "What's PLS?" Okay, cool. All right, good. And show of hands, who's quant focused versus qual focused? Quant? Qual. Okay, that's about right for an SEM bootcamp. For those who are purely qual focused, this will be enlightening. Maybe not useful, but enlightening. I do both. Actually, most of my research is qualitative, which is weird because I'm a quant person. Okay, good to know. Quick about me, super quick, just so you know who you're dealing with. Got my undergrad and master's at BYU and did my PhD at Case Western Reserve University. I am a gymnast. That's not me, that's Jake Felton. We look really similar from about here up. And I do gymnastics for fun with my daughters. It's great. I've lived all over. This is my 31st home. I lived in Japan for 3 years, Malaysia for 2 years, even Mississippi, all over. DC, Quantico, good places. Let's see, cows. This is my family, not cows. This is the cow. My family, my daughters. I have 4 daughters, beautiful wife, and they keep me busy. Let's see, the cows. Let's get to the cow. I have 4 companies right now, plus I have a real job. One of them is a cow company. We track cattle. It's a cow analytics company. Another one's a dream analytics company. We analyze dreams. Another one is a medical mixed reality company. We create augmented reality applications for surgeons and for the operating room. And then my wife just started this one, Dollar for Good, which is a $1 a day charity where you can donate. It's not up yet, and I'm not asking for donations. I'm just saying this is stuff we do. And then I make video games for fun, like Silver 16. Anyway, that's me. And I teach statistics. Actually, I'm in information systems. That's my major. That's what I teach at BYU. I don't teach any statistics at BYU. They do not use me in that way. I only teach it at Case Western and during this boot camp. But I do have a large YouTube presence. I do want to know, honestly, who has never seen one of my YouTube videos. There's got to be at least, yes, thank you. Okay, so there are 200 plus videos on YouTube, millions of views. It's kind of weird for a SEM to have a following, but there's a following. Anyway, so we do a lot with YouTube. Disclaimer. I used to work on a golf course. And I did the lawns. I would aerate the greens. Statistics is a lot like a golf course. It's enormous. There's so many different aspects of statistics, like tons and tons and tons. In fact, we don't have anyone from the stats department here, right? Last year we did, and that was awkward because I kept second guessing myself. But statistics is this massive field, and I don't know it all. When you aerate a green, you make little holes in the green that are like an inch in diameter. My knowledge of statistics is like that one aerated hole in the entire field of statistics. And so I know SEM pretty dang good. I know PLS okay-ish, okay enough to teach it. But anything outside of my expertise, I will give you either a really good educated guess, or I'll be like, anyone know the answer to that one? So if I don't know the answer, don't be like, oh, he's a total fraud, because then you'd be calling me out. I am a total fraud. But no, there's some things I don't know about statistics. Like someone asked me the other day, do you know how to do multi-level moderated mediated moderation in M+? Nope. Don't. Never done it. Okay. Here's what we're gonna do, the plan. We have 3 days, 3 hours in the morning, 3 hours in the afternoon. We have a 2-hour lunch break. That is intentional. So you can catch up on all your email. You can catch up on your work. Let's say we learned something in the morning. You're like, I need to apply that right now before I forget it. You can apply it during lunch. and so I can meet with you one-on-one if there's time. I do plan on meeting with you if you need me one-on-one to help you out, and I'm hoping even today at the end of the day I'll have time to take someone's data and plow through it and do an EFA for them. The 3 days will cover stats, factor analysis, and causal models, including PLS on Saturday. We usually end early on Saturdays. I don't know if we will this time because we're adding PLS. But if we end early, fabulous. If we don't, you got me. The protocol in this bootcamp is you are welcome to follow along, and I hope you will follow along, especially with your own data. That'd be awesome if you have your own data. If you don't, I have data. It's in that folder I just emailed out. You're welcome to use that data. We don't have time to like keep everybody with us lockstep. There's just no possible way we can plow through essentially 3 semesters worth of statistics in 3 days if I'm keeping everybody lockstep with me. But those who want to follow along, please try. And I will go slow enough to keep people with me who are feeling comfortable. If you're feeling totally lost and I'm going way too fast for you, just watch. And then if you want to hang out with me during lunch or afterwards, we can hang out and we can get you caught up to speed. If you're having tons of technical problems with the software, just give it up for now and watch, so we don't have to spend too much time on troubleshooting. If it's one small thing, let's handle it, keep you up to speed. But if it's feeling like you're impeding the class, you are. So be patient and just watch. This is mostly a how-to bootcamp. This is not meant to be a discourse on statistics. So most of what we'll do, I have slides for, but we're actually going to just be in the software. And then we'll go back to the slides and see what we missed. Please do feel free to ask questions about the concepts and the topics. Theoretical questions are fine. Mechanical questions, those are fine. I can answer most of those. But mostly what we're doing here is how do you do this stuff? And feel free to help others. If somebody gets lost and you know how to fix it for them. There are some resources for you. The Stat Wiki, right there. It's where I put a bunch of stuff, including videos, in fact, I should just show you. Let me go to the home page actually. Let me go here. Here's the Stat Wiki, for those who don't know. It's just where I put all the statistics stuff I do. And it has navigation here on the left. Today we're going to do data screening, for example. We'll go to the data screening. Here are the contents, all the stuff we could cover. One of the most useful is the general guidelines section. This has a bunch of just miscellaneous stuff, such as how to start every research project, and how to develop a quantitative model, what to do between gathering your data and testing your model, how to design a survey. This is the one we're going to focus on the most right here, is orders of operation. What am I supposed to do? I've got my data now. What are the exact steps in order that I need to take in order to go from having data to testing my hypotheses? So this is what we're going to do during the bootcamp, is this stuff. There's also newly added since last year a references section, which I have been extremely weak on in the past. This has references, all the references I use to justify statistical decisions. If I say this meets whatever threshold, there's a citation for that. Okay. Gasconation, the YouTube channel, that should be useful. That's where I'm going to post all these videos when I'm done. The Google Drive folder, there's a link there if you couldn't find it in the email. And all the slides, all the data, all the models we're going to use during this bootcamp, I'll save into that Google Drive folder so you will have access to it. For example, if you have been following along and you just couldn't get past this one little bump, I'll save my current model in that folder, and then you can go access that model, and it'll be working if yours wasn't, and you can keep up with us. Printers are on the 5th floor, east side. East side printers. Bathrooms are also on the east side on every floor. So if you need the bathrooms, that way. Or if you want the cleaner bathrooms, that way. There's a new building over there. Over there? Okay. Over there. I've only been here for ever. I'm still getting used to the directions. So clean new bathrooms over there in the new building. Okay, so today, here's what we're going to cover today. Somehow I missed EFA. Also EFA. We're going to do some basic statistics because there were some of us who we need to sort of get all on the same page of understanding the basics of statistics. So for some of you, this is going to be total review, snoozer, which is fine. Do email, do Facebook. Don't like record a podcast right now, but anything else is cool. If you've got this, don't feel like you got to be paying attention and staying awake. You're welcome to zone out. But then we're going to cover things like missing data, anything data issues, and then how to test your hypotheses. And then exploratory factor analysis this afternoon after lunch. And here is the model roughly that we'll be playing with. For those who aren't familiar with SEM, SEM allows you to test complex models. Each of these boxes would represent some sort of construct, some variable that we want to either predict or use to explain something else. And SEM allows you to test this entire model simultaneously, whereas older methods like linear regression or ANOVAs or t-tests only allow for fairly simplistic models. You can't test things like mediation and moderation at the same time while controlling for confounding effects, whereas SEM allows you to do that. So the data we'll be using is just some data I collected a long time ago about how people use Excel. Super exciting, sexy data. It's about the user themselves, how playful they are with their use of Excel, which sounds silly, how innovative they feel when they're doing it, how good information they get out of it, their personal anxiety when they use computers. What else do I have in here? The extent to which they use all features of Excel, things like that. So it's just about Excel and the users. And that's it. Okay, so that's all the non-content. Anything before we get going? Anything from remote folks as well before we get going? Because now it's just content moving forward. Okay, here we go. Here we go. So let's open up the data. Like I said, I have a bunch of slides here, but let's just open the data and start doing what we do. I should show you, actually, I should show you even before you open your data. You're welcome to open it, but I'm going to show you where do you get data. This data I obtained via Qualtrics. You don't have to go to Qualtrics right now. I'm just showing you. Most of your data will come from surveys if you're a quantitative scholar. And the survey, a good survey service is Qualtrics, actually created by a BYU grad. And I have a bunch of surveys in here. Let's see. Well, I'll just pick one right up here. Let's see, this one has 50. But what you can do is you send out your survey, you get data. Once you get the data, you click on data analysis and you import or export your data. I would go to export data and download it as an SPSS file. And once I download that, you'll see how it comes out. Here we go. Here's what I get in return. This isn't the same data set you're using. I'm just showing you as an example of raw data, what it's going to look like. Some of you have already done this, and you are welcome to do email right now or whatever. It's opening. It's thinking. Oh, it's thinking a lot. SPSS is a heavy client. It's the Adobe of stats. Well, really SAS is the Adobe of stats. SAS. Okay, so what comes out in raw data form is this. A bunch of mess that I don't actually need. And what I would do is I would delete all the columns I don't need. You see, Qualtrics and other survey services, they record all sorts of stuff. That when you started, when you stopped, if you're done, what your IP address was, all this junk that you don't really need. And so you could delete all this. You don't need it. Does our original data, let's see, I'm going to open up our real data now. Here we go. In the data folder. And it's going to be Bootcamp Original, this one right here. Open that up. And here's where I'm going to start going a little slower, because how many of you are like going to try to follow along just so I know how fast, slow to go? Okay, so I'll go with you. So here's a partially cleaned data set. You saw the last one had a bunch of other stuff like IP address and start and stop times. I've cleaned all that stuff out of this one. And all you do to clean it out is you highlight the column, you right click it and hit clear. Don't do that with this data. Okay, first thing you should do, make sure you've saved this onto your computer. Excuse me, if you're using my data. If you're using your data, it should already be there. Okay, when you get your data back, typically you have, unless you forced people to respond to every question, you'll have questions people didn't respond to. And you can't just run statistics on empty values. It doesn't work. You have to have numbers in there. And so what you have to do is take care of those missing values. So let's go find those missing values. Who here has never used SPSS? Okay. Okay. This is SPSS. Welcome. It is like TurboTax a little bit. A lot of menus and check boxes and option boxes and combo boxes and places to stick specific values, and depending on what you click and check and select, different things will happen. So let me zoom in here. Let's see. Here we go. If you go up to the top, you'll see Analyze. Click on Analyze. And here are all the things you can analyze, all sorts of stuff. And we'll play with some of this later today. What we're going to start with, is Descriptive Statistics. And we're going to go to Frequencies. This will tell us the number of missing values for every variable. For those who use syntax more than click menus, I will not be using syntax. I prefer to use the menu system. Okay, so what we need to do is figure out which variables we actually care about. And we need to actually do one more thing. For those who open this, does everybody see it the way I see it, or do you see it as like long questions? Long questions? All right, so two ways to fix that. The short way to fix that is to just right-click anywhere inside here and change it to display names instead of labels. But that's sort of a band-aid. It doesn't fix the problem. It happens every time. What you should do instead is, let's cancel this, go up to Edit, Options. Edit Options. And then in the Edit Options, in the General tab, in Variable Lists, change this to Display Names instead of labels. Let's change one more thing though.
And James, that'll actually, when you export it, then I'll actually change it when you export it
Yep.
to your output file.
Correct. It'll keep the labels, but it uses the name as the identifier, the display identifier. Go to the Output tab also, and make sure this says names and labels in these two areas. Names, labels, names, labels. This will solve some problems moving forward. So that was in the Output tab. Okay. Once you've done that, hit OK. It'll reset some things probably, and then we'll go back to Analyze and Frequencies, Descriptives and Frequencies. Now we're ready to roll. Okay. Which variables do we want to include? Whatever we have in our model. So we'll go back to our model. Here's our model. We need playfulness, anxiety, usefulness, comp use, information acquisition, decision quality. Anything that we're using, all of these variables, we have to assess whether they're missing values in these variables. So let's add them all. Was adoption one of them? It was not, so let's not include adoption. Anxiety was, I remember that one. If you just click and then hold shift and click again, it'll select everything that spanned there, and you can push it over. Atypical use was not. one of them. Comp use was design expectations fit was not. Efficacy was not. You know what we should really do? Let's do this. We're going to go over, close that. Go to the variable view down at the bottom. There's a data view and a variable view. We're just going to get rid of the variables we don't care about because they're in our way. We're not going to use them for analysis anyway. We'll save this as a different data set so we don't overwrite the original. But we don't use adoption, so let's get rid of it. Right-click, clear. We don't use atypical use. Clear. Design expectations fit. Efficacy. Did we use ease of use?
We
Nope.
use atypical use, I think. Do we?
We did?
No.
Oh no, anxiety is it. Yeah. So. You sound like the voice of God. You're coming out of the speakers in our room. All right. It happens occasionally here at BYU. It is a religious school. Sometimes I'll say something in class and I'll be like, no, he's wrong. Sorry. All right, let's see. Get struck down here. Enjoyment, we do not use enjoyment either, so I'm gonna get rid of enjoyment. Multiplicity, multi-something, get rid of that. We use playful, so I'm gonna keep playful. Repurchase intention, nope, not using that. Skill acquisition, I don't think that was in there. All right, let's see, skill acquisition, nope. Social desirability is in here, so we'll keep that. System satisfaction, nope. Information acquisition, yes. And decision quality, yes. Unfaithfulness. This is unfaithfulness to the software, not in relationships. I said, anyone not know what the IRB is? IRB, yeah, it's the human protocol. They make sure you don't violate humans. And here at BYU, they're particularly sensitive. And I submitted a paper, this paper, in order to collect data. It was called The Virtue of Unfaithfulness. And they didn't like that. Here at BYU. I told them, no, it's being unfaithful to your computer, not with your computer. Okay, let's see. Usefulness, we do. Comp score. We don't need that. Age, education, experience. We have age, experience, but not education. We can drop education if we want. Experience, gender, frequency, child order. We're actually going to keep this for some other analyses. So keep child order in there. And I'm going to keep these others for some other things. So here's what we have left. If you were trying to follow along, we have anxiety, comp use, playfulness, social desirability, information acquisition, decision quality, usefulness, and then all these little ones at the bottom. And I'm going to save this as a new file. Save as. Let's call this the trimmed, and I'll call it 2018.
Did you ever change the ID name to a long string rather than a number?
Right, so up here in the ID, it's just a string. I don't mess with it. You could, if you wanted, just change it to 1, 2, 3, 4, 5, 6 unique auto number, but I don't, it's already unique. Yeah, I do keep it though. Because occasionally you'll take your data out of SPSS and then you'll bring it back in. And if you have somehow messed up the order when it was out, then when you bring it back in, everything's all skew-wampus. Which reminds me, last year we had a hard of hearing attendant and I said skew-wampus. And the ASL, the translator was like, I gave him some good ones after that. Higgledy-piggledy, that was a good one. Anyway, so they just started going like this. Anyway, okay, sorry, back to work. There's a chat, here we go. At this point, do we include all the items for all the factors in the model, IVs, DVs, mediators, motors? Yeah, we're gonna keep everything, Rob. Everything we're gonna use in model, we're gonna keep it for now. And we wanna analyze all of it. So, analyze. We're finally going to get to some analysis. Descriptives, frequencies. Okay. Once you click on frequencies, this dialog box opens up. we're going to add, now that we have it, we're going to add everything, essentially. Everything we're going to use, which is down to there. Everything from anxiety 1 to frequency. Throw that over there. And then over here in the statistics button, there's a bunch of stuff we can click on. For now, go ahead and click on skewness and kurtosis. We'll talk about it in a little bit. Skewness and kurtosis, right there. And then hit continue. Charts, we don't need anything right now, although we could. We'll do that later. Format, style, bootstrap, we're good. Okay, hit OK. It's going to think, and then it's going to produce this right here. And this is a massive table. I'm just going to copy this table out to Excel because it's easier to quickly scan. So throw this into Excel. And once it's in Excel, we can start playing with it. First off, we want to know which variables have missing values. And we can see pretty quickly. Let me zoom in. My zoom on Excel doesn't. There we go. Okay. None of the anxiety indicators have missing values. None of the computes do, but playfulness is missing a few. Check this out. Playful 1 through 7, all of them have some missing values. Let's go look at playful real quick. Over here. And go over to playful. Here's playful right here. Let's just sort this. You're going to right click the top and go to sort ascending. And lo and behold, we have 2 rows. Each row represents a participant in this study. 2 rows missing quite a bit of data, actually. Let's see, let me scroll over. So it looks like what happened is, it looks like they started the survey, and then their kids started screaming or something, and they had to leave the survey, and they didn't finish. So what can we do with these guys? They only gave us data for anxiety and comp use. Yeah, I would just get rid of them. We have 381 respondents, which is a good enough sample size for almost anything you want to do. Removing 2 people is not going to change much of anything. What will, like, where's the threshold? Where do you say, oh, that's too many? It's about 10% of your data set. So if we had to remove 40, that would be a problem. But less than 40, it's like, not so big a deal. Is that locked? Oh, you got it? Come on in. You're here for the boot camp, right? Oh, good. I should have said something else. Dang it. Next time. Remind me. You're here for the Girl Scout cookies, right? No? That's got to be better than that. Something MLM. I'll think of something. All right, so I'm going to select those 2. I'm going to select these 2 rows, and I'm just going to right-click and hit clear. These 2 are useless to us.
Sorry, could you repeat? If it's less than 40%, do not remove.
No, if it's less than 10%, you're welcome to remove those without any. There's no major effect on your data set.
Each row, how many?
Okay, so then what is the criteria for missing? What if they took all of the survey except the last questions? Well, then keep them. We'll actually see a couple like that in a minute.
So what's that criteria?
Again, it's 10%. If they have failed to take 10% of your survey or more, then you're welcome to drop them. If they've taken more than, if they've taken 90% of your survey, keep them. If they've taken less than 90%, you're welcome to drop them.
So should we need to address this part of criteria on our report?
Yeah, so when you're reporting this, what do you say? You say we started with 381 respondents, but not all of them were actually usable. For example, in 2 cases, we had them submit a largely incomplete survey. So we removed those 2 cases. You may say they only finished 5% of the survey or something like that. And so we removed them. They were useless. Don't say they were useless.
We should put a citation.
No citation needed for that. If you want to cite something, if I say anything, you're like, who can I trust other than Gaskin? Cite Hare, Joe Hare. He'll back me up with almost anything. Almost anything I say. Yeah.
Just sorry, follow up since they stopped you. Can you quickly repeat what you did on the frequency? So you do check for kurtosis
And skewness, and then that's it, and then hit OK. Yeah.
Okay.
And then once you get here, if you find some that are missing values, like we did, we found that playfulness is missing quite a bit, or each one is missing 2. Then just sort playfulness at the top, right click, sort ascending, and it'll bring up those blank ones to the top. In this case, it was just they didn't finish the survey. So I'm going to delete those, right click, clear. Over here in the remote folks, you guys have some questions. And we would find a site for the 10% on the Gascon Nation website? Yes. I trust you completely, by the way. Can we cite this class as authoritative? You can. You can cite anything. I mean, you can. It's the reliability of that citation that is in question. Typically, scholarly works are considered the most rigorous citation, followed by books, followed by conferences, followed by personal communications. This would be considered a personal communication. Okay. So that was those 2. Let's find out what else is missing data. Playfulness 4 was missing more than just those 2. So let's sort playfulness 4. Here's play 4, right click, sort ascending. Here are these 2 at the top. Just these 2 missing. It looks like they took the rest of the survey, yeah? Most of the survey. They're missing a social desirability question. But they took more than 90% of the survey. So what do we do with this? The best thing, I think, when you're collecting data in this way, where you have like 7 different questions, all asking about the same thing. In fact, if we were to go look at the wording of these questions, let's do that. If you double click on Playful 4, it'll take you over here to the variable view. And I'm gonna go look at this real quick. Whoa, Control Z. Here we go. Zoom in. Here's Playful 4 and 2 and 1. If we look at these in order, Playful 1, I'm spontaneous when I interact with Excel. I'm imaginative, I'm playful, I'm flexible, I'm inventive, I'm creative, I'm original. These are all saying sort of the same thing. When I play with Excel, I'm playing. I'm innovative and I'm creative when I'm using Excel. These are all saying roughly the same thing. So the best thing I think to do when you have missing values in a set of variables like this is not to replace those values with the median or with the mean, but to just look at how they answered the other questions. So this person, this row, they answered 2, 2, 2, blank, 2, 2, 2. I bet we could guess what they would have put for Playful 4. I'm pretty sure it's 2. So I'm gonna put a 2 there. And someone's gonna be like, oh, no, you're cooking the books. You're not. This is an educated guess. Also, this 1 value will not have any effect on your book. It will have nominal, non-significant effects on your data set, especially since we have 379 rows left. It's not going to have a big effect. Plus, we're right. What do you think this guy would have answered?
3.
Obviously 3, right? So we'll put a 3 there. Okay, let's go back to this table.
We can address this problem.
So yeah, what do you report? Thank you for asking each time. What do you report in your paper? You say a few respondents failed to answer some questions on our survey, likely due to neglect. They just overlooked it because they answered the rest of the survey. So for those missing values, we imputed with known values. That's the phrase, known values. So we saw what they answered for the other questions that were like it, and we used that to fill in the blanks. So we use known value replacement.
Is one way more preferable than the other?
One approach?
Known value,
Yeah, so
median, or
they're sort of levels of the approaches you can take. When it's like this with reflective scales, we'll talk about reflective versus formative in a little bit, but when you have a scale that asks essentially the same thing over and over again, this is the preferred method. To use known values because it's going to be the most accurate. If we had instead used the mean, check it out. Let's see. Let's grab. I'm just going to don't do this with me. I'm just gonna copy this over and paste it real quick. The mean of this set of values is 3.09, which for case 2 would have been great, but for case 1 that would have been incorrect. Would have added error, artificial error.
When would you lean towards something like thermal imputation maximum likelihood instead of this?
So there are algorithmic approaches you can take to replace missing values. Those are most useful when you're using individual observed constructs like income, number of employees, things that are a single value that have no known sort of proxies. So when they have to be calculated in order to be correct, you'd use something like a regression or an ML to guess, essentially algorithmically guess with the least error what the missing value would be. In the case of categorical variables like gender and marital status, that is going to be harder to guess. Like I would hesitate to even attempt it. Also, you don't want to put the average, obviously, for gender or for marital status. Average actually makes no sense at all for marital status, unless you only have a binary, but even then it has to be one or the other. So in those cases, either leave it blank or don't use them in a particular analysis that requires you to use gender or marital status or company industry or something like that. Okay, let's fix the remainder. So we fixed all of playfulness. We go over to social desirability. Looks like we have a few, oh, shnikes. We have a few, look at this, social desirability 7 is a major problem. Social desirability 1, 2, 3, let's do this. Let's go to 2. Social, actually, let's just sort, let's do 7. That's the one missing the most. Okay, social desirability 7, here you are. Sort ascending, holy cow. People didn't like that question. What was that question? All right, let me zoom in here. Oh, dang it. Okay. This question is, there have been occasions when I took advantage of someone. You can see why people might not want to answer this question, right? And I remember in the survey, I intentionally did not force the respondents to respond to this question. Because what will happen is, if you have a question in here that could implicate them and you force them to respond to it, they'll just stop taking your survey. And they'll try to recant everything that they already entered so that you can't catch them in their crime. You'll notice social desirability is kind of a funny one. It starts here. I'm always willing to admit when I make a mistake. People will answer that one. I always try to practice what I preach. I never resent being asked to return a favor. I've never been irked when people express ideas different from my own. I have never deliberately said something that hurts someone's feelings. I like to gossip at times. That's another one that people tend not to answer. I took advantage of someone. I sometimes try to get even rather than to forgive and forget. At times, I have really insisted on having things my own way. There have been occasions when I felt like smashing things. This is a special construct that we'll talk more about tomorrow, but it essentially captures the extent to which you are willing to answer things in the socially desirable way, because there is a correct way to answer all of these questions. So we're capturing that. Anyway, we can see why people might have not wanted to answer number 7. What do we do though? Is it more than 10% missing? Yeah, it's 40, whatever it was, 47 or 48 or whatever, or more. It's useless to us. I mean, that's a lot of data we're missing. That's a lot. So essentially, we can't use it. I'm going to just delete it. Clear. We no longer have number 7. What would happen if we imputed all of that with the average? It would totally dilute things. Yeah. It would make that variable, again, useless because of this. Well, I wish I could draw. It'll make it useless because if you enter the same value for a bunch of respondents, then the XY graphs will flatten out to match that mode.
So how bad removing one question impacts the availability of the question?
What is the threshold? Like where we say it is too much. It's about 10%. There are actually different published thresholds, as is the case with almost all statistics. I've seen 5, 10, and I've even seen 20%. 20% is really pushing it, though. I mean, that's a lot of replacing. And I feel like I'd be cooking the books a bit if I replaced 20%. My personal threshold, 5% max.
Is that the question?
For either a column or a row. Either way, 5%, that's a lot.
Hypothetically.
Yeah.
If you have 10, you have a social desirability with 10 different, if you have, or 10 different whatever,
Items.
thank you.
Yeah.
If you were the other way and you had 5, and now you have a little bit more materiality, you delete one of them.
Okay. Yeah, the question is how few items can I have per construct? And if this were a construct that only had 4 items, each item is a column here. Each construct is this whole set here. If I only had 4 of these, how willing would I be to delete one? I'd be less willing. I might raise my personal maximum threshold from 5 to 10. Yeah, because you want to do your best to keep a robust construct. Yeah.
What if hypothetically,
Yeah.
you decided not to delete it at this point?
If we decided not to delete at this point, it would still be useless to us later. We could include it in our analyses, and what will happen is when the analyses are running, everyone who didn't respond to that question will be excluded from that particular analysis if we're using that variable.
But if you hypothetically did go ahead and impute it,
Yeah.
because it was less than 5%.
Yeah, if it was missing less than 5%,
Because it-
you're welcome to impute.
Right.
And let me show you how you do that with the mean or median.
Well, that was the other question. So if the percentage of, so you have over 300 some odd respondents.
Yeah.
And there's 40 something missing.
Yeah.
Math.
That's more than 10% missing.
It's
Yeah.
more than 10%.
But less than 20%.
But less than 20.
So you can cite whoever you want.
Like here.
Yeah. Well, I don't know if Hare says 20.
It has a chart.
Yeah, there's a chart in there somewhere. Talks about missing.
Yeah.
Okay. Here we go. Yes.
Just to piggyback off of Dan's question.
Yeah.
On the items, let's say you only had 3 social desirable items. There's a reason why you don't want only 2. Right?
Yeah, there's a reason why we don't want just 2 items on a factor, on a latent factor. The way latent factors work is you don't measure the thing directly. A latent factor, like social desirability, is measured indirectly by all these different items that sort of surround the idea. And if we look at essentially the centroid of responses, the middle of those responses, we can see the core, the kernel of the construct. And we can use that sort of, it's called a factor score. We can use that score as a representation of the value of that construct we didn't actually observe. When you only have 2 points, it's just the middle of those. And so it's less accurate. If you had 3 points, then it sort of converges a little bit better. 4 points, oh, it's over here, right? It converges more precisely, removes error, the more items you have. The fewer items, the more error. Yeah.
So this just seems early to take something out. So
Right,
if I
and-
didn't, let's just say hypothetically, if percent left it.
Yeah,
Sorry.
you're good.
Am I, or would this person be compromising? Would it take 46 of the people out of everything else that you do?
Right, so the risk of leaving in something like this at this point, with so many missing, is that any analysis that uses social desirability 7 is now compromised by 47, or however many we were missing, 48 missing. So there'll be 48 respondents not included in that particular analysis. Yeah.
Would it take everything out for those 40, or just the social desirability?
That's a good question. The question was, will it take the respondents out for every piece of that analysis or just for the parts including social desirability 7? I don't know the answer to that.
Are you just removing the column for 7?
Just removing the
So
column.
taking out
Well, no, so in this case, I removed, the column. And so, yeah, it's going to remove we're actually not going to use it. But the question is, if we keep it in and we run an analysis with a bunch of variables, including social desirability 7, will all 48 respondents be missing for all of it or just for a piece of it? And I don't know the answer to that. I'm sorry. Yeah.
Wouldn't that be the case if you, it would be the case if you were to use that, we moved on to confirmatory factor analysis.
In confirmatory factor analysis, yeah, it'll just use it for the piece that social desirability 7 is a part of.
Right, so those, for example, won't be.
They just won't be part of that
in any of it.
more complex model. Yeah. Okay. But my recommendation, if you have something that's that dramatically off, is just remove it from the beginning. Yeah. Okay. Here we go. That was that one. Let's go to, we got to fix the rest here. Social desirability 10 and 3. I'm going to sort. I'm going to sort by 3. They didn't want to answer. Let's see. There are several people who didn't want to answer that question. What do we do with it? We can use known values. Although, except you see, let's look at this. Let's see, from social desirability 1 through 10 here. Is there a consistent? And there isn't really a consistent response here. The question is, do I use a median of these or a mean of these, or do I use a mean of these? And the answer is you can use either, whichever feels more logical.
So that means that there's no correct answer or no.
Both correct.
No standard.
There's no standard practice. Yeah, and you'll see actually when we go do this. Check this out. If we were to go to analyze and not analyze, sorry, transform, replace missing values. Transform, replace missing values. Right here. There are actually multiple routes you can take. So over here, if I were to throw in where is it? There it is, social desirability 3. If I were to throw this in here, it says, well, which method do you want to use? There are different methods to replace these values. You pick one. It doesn't recommend the best one. So you just got to pick. We can do the mean of the series, that's the column. We do the median and mean of nearby points, and we can say how many points, how many different points of reference do you want, and we can do something more algorithmic like a linear trend. So we can use any of those.
If you can just clarify that. So what you did before was basically the
I used known values before.
known values. Right?
Yeah, that's right. Which doesn't use, which isn't, the closest here would be median of nearby points. Yeah. Which
What's
is
linear interpolation?
This is more of a regression-ish approach.
Okay.
It says, well, if there are other variables, how to say this? Can we predict the value is the question, using other variables. Exactly, yeah.
And which one would you, I mean?
For this one, I'd use median of nearby points. And instead of mean works well for continuous scales like income, age. Median's better for more ordinal Likert type scales. So how many points nearby? I'll just use the closest 4. Hopefully that should do it.
For 4.
2 to the left, 2 to the right.
Okay.
Yeah. And since it's number 3, that'd be Soc 1, Soc 2, Soc 4, Soc 5. And the thing though is I don't want to run this because what this does is it replaces the existing column and deletes the wording of the question. I'd rather not do that. So I'm just going to enter these values manually. So I'm going to hit cancel there. Go look at these and say 4 and 2, 3. This is about a 3. This is about a 2, about a 3, and about a 3. Just by looking at these right here. And that's not perfect. Do I care if it's perfect? It's 4 values. It's 1 value per person out of a bunch. Is it going to make a huge difference? No, not if I'm that close. It's not. And so what you report, you'd say we replaced with a median of nearby points. Here's another one down here. If I go to Soc 2, We're almost done with these. This person answered pretty consistently here, 2, 2, 2, 2, 2, and then a 4 and a 4, and a 4 and a 4. I'm going to put a 2 in here. There's a chat question. If some survey questions are open-ended text questions, how to deal with these questions in SPSS? Open-ended text questions are not ideal for quantitative analysis. They're better for qualitative analysis, so I would not deal with them in SPSS. I would ignore them in here. The only exception would be if you wanted to sort of code the text and then extract new variables from that text. So let's say the text was about your review of an Amazon product. If I wanted to code out something like sentiment, how positive or negative the sentiment was, or frequency of negative words or something like that, I'd create a new variable to represent that quantitative aspect of the qualitative data. Okay, I think we got most of them here. 3, social desirability. 4, did we fix that? Sort ascending. It's just 1 here. 5, 4, 2, 1. That's interesting. 4, 4, 4. It's fine. All right, so what would we put here? I'll put a 3 because it's in the middle of 5, 4, 3, 2, 1. And it's not going to make a big difference there. Anything else? We got rid of that one. Social desirability 10. We'll have to fix that one. Now, you may think this takes forever, but when you're not doing it in a classroom setting, it's fairly quickly. It's fairly quick. This guy answered 2, 3, 3, 3, 4, 3. Let's say 3 for that one. Okay, anyone else? These 2s we already took care of because they were those cases that were missing all of them. Cool, looks like we got it all. Yeah.
So James, when you do a survey, you never force people to answer.
Occasionally I do force responses for certain questions. For the dependent variable, I always force response. So in this case, again, for those who are catching up to theorizing and whatnot, in this model, the dependent variables are the ones at the end, information acquisition, decision quality. These are the things I really want to explain and predict. These are the things my research questions are about. If I don't get data on these, then that person is useless. Even if they answer the rest of the survey and then they skip the last part with the dependent variables, they're useless to me because I want to predict the dependent variables. So,
Hello.
Yes.
Hello, James.
Yes.
Yes. My question is on the model. If I'm a researcher or a consultant, I'm given a model like this.
Yes.
What I assume to be a mixed relationship, maybe between independent variable and dependent variable. To what extent can I add like an arrow or something, to link the 2 variables? That's number 1. Number 2 question is
I didn't understand the first one. I'm sorry. What's the first question?
My question is, if you are a researcher and given a model like this,
yes,
with what you deem as lacking, what do you call it, a relationship between 2 variables, for example, playfulness,
yes,
and that information acquisition, that arrow is missing.
Yes, correct.
The original. So, to what extent can you manipulate it? Can you add to it, or if you can, or to remove an arrow or something like that?
Oh, add and remove arrows in a model? Yeah, so if you're a consultant, scholar, or researcher, and you've been given a model you need to test, what liberty do you have to add or remove variable pathways?
Yes.
It totally depends on the client, obviously. What I would do, and I've done this for a few clients, is they've given me things, they've given me research questions, and then I've been at liberty to answer those research questions in whatever way I deemed most appropriate. And that's usually the case. Very rarely will you be given a model that must be tested unchanged. Because in SEM in particular, even though you go in with an a priori theory, there are certain global criteria that must be met in order to have any confidence in the final model. And one of those global criteria is, does the model hold up to the data? And if it doesn't, are there paths missing that should be there? And if there are paths missing that should be there, then they must be added, or else you can have no confidence in the findings.
Right. Thank you.
You're welcome. We'll talk more about that when we talk about model fit. But yeah, that's one of the global criteria. Okay.
Just a quick
Yeah.
question on technical operations.
Yeah.
Why would you use the descriptive frequency method instead of using the missing value analysis? Okay.
Oh, there's a missing value analysis?
Yeah, because that actually gives you the percentage under.
Cool. Where is it? Hey, that's new.
Yeah.
Whoa.
That's actually pretty slick.
I want to see that.
Because that actually gives you the percentage of each item's, the percentage of.
Cool.
Okay.
That's awesome.
Where is it? Where is it?
Yeah, it's in, if you go to analyze, it's this new feature right here. This must be new as of 25. Yeah.
24.
Oh, 24 had it? Cool. Missing value analysis.
And I don't think it appears in the basic package.
Okay. Let me check this out. Let's see what happens. Cool.
So you get you the missing value and the percentage. So you can actually
Nice.
see if it's 3%, 10%.
And you can see the means if you want to impute with the means. So cool. Wait up. Missing count. All right. Are we missing any at this point? No, we've covered them all. Sweet. But if there had been any missing, it would show up. That's awesome. Thanks. I learned something new. Woohoo! I might make a video about that. Okay. All right. I'll call it the Big Tasty. Here we go. Sorry, inside joke. Sorry, inside joke. Let's see. In an academic setting, am I right to assume that if the model is kept the same, we don't have to hypothesize on every regression line? Yeah. You again, depends on the flexibility you've been given from the client. If they put a line there, they probably want it assessed. But if they just have a research question and they have a suggested model, well, then you can make up which lines are most important, and you can exclude the ones that you find to be less important. In the specific hypothetical scenario you're talking about, you can choose a set of paths. You don't have to choose them all. Just as a FYI to everyone else, not from Case Western, those who are from Case Western are completing a capstone assignment, and so half of them are here to push them forward in that capstone assignment. And so they may be asking hypothetical questions related to this capstone that I'm not allowed to answer directly. But that's the inside joke we're all prancing around. That's why they keep using the word hypothetical.
So what was that hypothetical type question?
Yeah. His question was, do we have to have a hypothesis for every line in the model? And the answer is no. Pick the ones you want. Make sure you're representative. Okay. Have some mediation, have some moderation. Here we go. So we're done with missing. Yes. Let's go back over here. So a little bit on the, I've talked around this a little bit. So when you have missing data, the problem is those values are useless to you. So you don't want to just leave it unaddressed. In particular, if you have a lot of missing data, then you end up biasing your analyses. Gender is one of those things, and gender, marital status, income, these are things that people tend to feel a little bit hesitant to answer on occasion. And so let's take gender, for example. If 95% of the males report their gender, but only 50% of the females report their gender, if you were to go either wipe out all of the female respondents or impute their gender, you would have very biased responses because you're only getting half of the females. So you have to be careful with missing data, because if you were to impute all of it, you actually end up having some response bias. Because if you imputed half as male, half as female, just to be average fair, that would be incorrect. You're entering and you're introducing error into your data. So watch out. We talked about this. Why not force them to answer gender?
Yeah.
Some people are very sensitive about gender questions. In particular, we can talk about other variables, but gender in particular is a sensitive question for some, and they do not like answering it.
Can you give a third response?
Prefer not to respond. You can. The trouble there, and I've debated this with this is it's like if you put a not applicable or other or something like that, some other option on any question, people will default to that if they have any hesitation on how to respond. And those values are essentially missing values because they're not part of the scale. So if somebody put rather not respond as gender, unless we're using that as a trait itself, like males are theoretically like this, females are theoretically like this, and people who don't like to respond are theoretically like this. Unless we use it like that, it is now useless. Yeah.
Isn't it useful when you're describing your demographics? Because I've seen a lot
Certainly.
of times, 10% decline to respond and that sort of thing.
Yeah, and you can throw that in the report. One thing I like to do with questions like this that are like, well, I don't know how to respond to that, or I don't feel comfortable responding to that. Something like gender, you can have a masculinity or femininity scale, or an identification scale where it's not categorizing me. It's, this is how I truly feel about myself. And then they can answer more accurately. The reason people don't like to answer these questions is because they know they're giving an error-prone answer. It's like, I'm male, but, right? Or I'm female, but it's like, this isn't the accurate response for me, so I'm entering error into your data. I know they're not thinking that, but that is what's going on. I was like, I don't have a good response for this. So how am I supposed to answer it? Okay. Talked about this. I put 10% here. I prefer less than 5%. We talked about that. Here are the methods we talked about. We didn't talk about option 1. Option 1 is a good option when you have a lot of data. Option 1 is you don't use any missing values. Any cases that have missing values, you just lop them off the data set. When you have 500 respondents, this is cool. No problem. Unless it's like 50 people that didn't answer one question. Well, then don't. Again, it's 10% rule. Don't get rid of a lot of people willy-nilly, but when you have a lot of data, you have a lot more flexibility to do that because you're not going to bias the data by removing a very small fraction of the respondents. We talked a lot about option 2, which is my preferred method, and then option 3, which would be a calculated approach using the mean, using the median, or some sort of algorithmic approach to predicting what value should be there. Best method though, prevention. We should talk about this. It's not quantitative analysis, but it is good prep for quantitative analysis. Short surveys are better. You ever take a survey that's like 15 minutes long? Or even you ever get an email that says, this survey should only take you 20 minutes. Like, done. I'm not, nope. Not answering that survey. If it says 3 to 5 minutes, I'll do it, sure. Otherwise, I ain't got time for that. Easy to understand questions. Make sure you pre-test your survey questions. If you're developing your own survey, don't just be like, yeah, this makes sense to me, go, and like send it out. First off, you gotta get IRB approval. But also, you should pre-test it. Have your buddy who never agrees with you on anything read through it. And then you'll find the holes and it'll be surprising to you until you see it. And then you'll be like, oh yeah, I can see how that didn't make any sense. And also it'll help you catch those questions that are terrible. You ever take a survey that asks you something like this? Here's a good example. Who did you vote for in the last election? First off, you shouldn't ask that question in the survey. But if you did and you only listed the candidates, what if this person didn't vote? How do they answer that question? Or you ever see the question, I have great love and respect for my spouse. What if you're not married? Or I get embarrassed when I pick my nose in public. What if I don't get embarrassed, but I do pick my nose? Or what if I don't pick my nose and I'm embarrassed anyway? It's like two different things you're asking at the same time. You can't do that. So what pre-testing will do is get rid of those questions that create error in your survey. And people just don't want to answer those questions, and so they'll skip them. There is forced completion, which has its drawbacks. If it's a question nobody wants to answer, you're going to get a lot of people dropping your survey. Bribing and motivating. It works. People want to finish that survey because they want to be entered into the iPad drawing. Digital rather than paper. This is an issue. I've done studies in gerontology because I work with a lot of different people from different fields, and we had to do paper surveys. But if you can avoid it, avoid paper surveys because those create error. this we talked about briefly. Put your dependent variables at the beginning. If somebody's going to answer your survey but quit, you want them to quit after they've answered the thing you really want to know about. Don't put your dependent variable at the very end of the survey, because they'll get tired and they'll be like, yeah, I don't know, whatever, and they'll quit. And you'll get everything except the thing you actually need. So put those at the beginning. And then sensitive items like income, gender, marital status, social desirability questions, put those at the very end of your survey. Anything about loyalty to your company, things that might implicate someone, put them at the very end. Because if they get there and they've answered everything else and they see that and they're like, oh, I don't feel comfortable answering this, and they quit, you still have all of their other responses. And so, whereas if you put that at the beginning, if the first question on a survey is, I like to get even rather than forgive and forget, you're done. Like, I'm not, what else is in this survey? Yeah.
So you can ask all the social desirability questions at the same time.
You can, at the very end. Yeah. Or you could randomize the whole thing. But then it's like weird every now and then. Yeah.
I use a control item that seems similar to the other. Like, I enjoy my favorite meal. And if people respond less than 3 or 4.
Yeah. Okay, this is great. It's called a trap, an attention trap. Yeah. So I think I have this here, the last one here. Attention traps. You want to make sure the data you're getting is good data. There are people who will just respond, yes, strongly agree, all the way across. But if you put questions in there like, I really enjoy my favorite meal, like who's going to say no to that, right? Or here's one, I regularly eat car tires for breakfast. No, nobody can strongly agree to that, right? Logically. And if they do, and it's true, do you really want them in your survey anyway? Anyway, so these are traps to make sure people are paying attention. What you don't want to do is something like, if you're paying attention, please answer strongly agree. Because nowadays, people know to look for those. In fact, if you use Amazon Mechanical Turk, which is a big service where you can send your survey out to millions of people and they'll answer your survey, there are people who will just Command F or Control F and search for the word attention or answer. And they'll find those ones, they'll answer those first, and then they'll go put someone agreed to everything else. So they'll still get paid. So anyway, put attention traps in there. I usually put 2 in mine. Somewhere towards the 1/3 and 2/3 mark. And then if they answer those incorrectly, then you know that they weren't paying attention.
So do you remove those? So in my survey, I think I had like 5 attention checks.
Yeah.
Because it was a crazy long survey.
That is a really long survey.
And I had some people fail like every single attention check and others that passed. So
if they fail, you remove the entire row. If they fail any of them,
I mean, I think failing one.
Failing one, what I would do,
okay.
I would check around it and see if everything else makes sense. And if everything else makes sense, it's like, they made a mistake. But if they even if they miss 2, I'd be hesitant to keep them. Yeah. Unless I only had 30 respondents, then I'd be really careful and check every response. Yeah.
I was just going to say the amount of attention traps. If you have, like, you would just have 2 of those, that's 8 in the whole survey.
Yeah, I just had 2 attention traps. Yeah. There are other ways to do it. You get a reverse coded questions, something like, I love my job is awesome, my coworkers are great, I hate my job. And if they answer, I hate my job the same way as I love my job, they weren't paying attention. You can take them out of your survey. In this data that you have, I don't think we have any reverse coded questions. I personally hate reverse coded questions because there are cultural and personal affinities for positive and negative sides of the scale. In the US, we're positive bias, and so we are more willing to answer strongly agree and somewhat agree than strongly disagree. Or maybe it's not the US, anyway, one of the cultures, it's like, we only answer positive. If we have a negative thing to say, it'll be somewhat disagree. It's not gonna ever be strongly disagree. So if you reverse the question, and they're supposed to answer strongly disagree, because it's the opposite, they're not going to. They're gonna create error. Anyway, we should look real quick in our data, see if there are any B-liners, anyone who answered just like all the same all the way across. with a data set this large, you don't want to like eyeball it. Your eyes are going to get tired. So one thing you could do is just check the standard deviations of rows. So I'm literally just going to copy the entire data set. Control A, Control C, copy that whole thing, and stick it over in Excel. You can actually do it in SPSS. I just don't want to. It's faster this way. And at the end of this data set, I'm going to get rid of these non-Likert scale, like all of these here, everything from AX onward. Get rid of those. And then, so these are just the Likert scale items here, except that first one. These ones here, all Likert scale, 5 points. So if they answered the same to everything, their standard deviation would be 0, right? Equals standard STD EV. And I'm going to use just all of it except these. Ah! Sorry, I pressed something. There we go. Everything there from C onward. Just the standard deviation. I use the S. You can use P if you want. It's not going to make a huge difference in this case because we're just looking for zeros. And so we're going to go look for zeros, or we can go like this. Highlight all of that and go to conditional formatting. Highlight cell rules. Less than. Anything less than 0.2. Let's see. It'll highlight in red. Oh, there's a 0. Look at that. 3s all the way across. This is number 130. So if we go over here to 130, here he is, 130, 3333333. I'm betting that's not how this person really felt, right? Can I delete him? Yes. What would I report? I'd report we found one case of a respondent, an unengaged respondent, somebody putting 3s for everything. We remove them. Anyone else? Let's see. So that's that guy. Anyone else? Why not just sort them? Because that gets rid of the order, and I want to know which number they are. Nope, no one else. Okay, so that's pretty good. There are other cases of unengaged responses, like somebody answering 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Those are really hard to catch, especially in a data set this large. You can look down here, but
Wall tracks, and some of those have a way of catching that Christmas tree pattern, 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Right. I wish. Do you know? Do they have a way to detect it? I don't know if they do.
I haven't checked.
Yeah. Eventually, we'll have smart enough systems to catch this for us. But for now, we're eyeballing it in the chat window. Doc, is there any way to copy over the column headings along with the data? The answer is yes. You have to export the data set instead of copying and pasting. So a bit of a pain. Okay, so just that one. Now let's say we do have a couple left in here who answered 1s and then 2s and then 3s all the way across. If it's 1 or 2 people, it's not going to matter. Not in this large of a data set. Is it going to be more than 1 or 2 people? Probably not. It's unlikely. Unless you have like really, really unreliable data source, like Mechanical Turk, or if you paid Qualtrics to go get you data. But you could stipulate in that contract that they have to find unengaged responses. And then they go through it manually or automatically if they have automatic ways to detect it. It wouldn't be hard to write some code. I won't do it right now.
James, I have a question.
Yeah.
What about manipulation check questions? Where should we place them in a survey, or how could we use them for validity of their answers?
Sure. So manipulation checks, for those who aren't familiar with experimental design, manipulation checks are variables that assess whether you actually manipulated what you thought you manipulated. So let's say you're giving a treatment of, I'm actually doing this right now. I'm going to share a cool study I have with you. I'm studying time dilation and how to design user interfaces to manipulate the perception of time contraction and dilation. so that user interfaces can be designed to speed up time or slow down time, depending on what's needed. Very theoretical, but very applicable if we figure it out. So we are creating user interfaces right now that are either very routine, habit forming, or very exciting, fun, gamified, or very distracting. There are many different levers. What we have to do is we have to check our manipulations. So before we collect any data, we need to go pre-test these different user interfaces and have people use the interfaces and then tell us, to what extent was this boring or habit forming or exciting or routine or whatever it is we're trying to manipulate. And if they say, oh, the routine one was very boring, well, then we haven't done our job right, because we weren't going for boring, we were going for routine, very habit forming. And so our manipulation is wrong. So this is sort of off topic, but it is addressing the question. You have to collect data on that to see if you actually manipulated what you thought you manipulated. Did that answer your question?
Yes, thank you.
Okay. Go ahead and mute your mic if you wouldn't mind. Thanks. Another question up here. If we have time, could you show up how to export the data with the column headings? Sure, that's easy enough. If you want to export your whole data set in SPSS to Excel, go to File and Export and Excel, right there. And this will export the whole data set. And make sure that this checkbox right here, variable names, is checked. If you want to keep the variable values as well, you're welcome to. The variable values, not values, labels, excuse me, is the wording of the survey question. Those are the labels. So you can check that as well. Okay. So that's unengaged respondents. We found those. Let's go down. And we talked about those. And that's that. Now we need to look at the normality. So we sort of addressed problematic data, problematic respondents, people who haven't responded to every question or who have responded in an unengaged manner. Now we need to look at the quality of the responses given and how normally distributed those responses are. In statistics, you'll remember this from your stats 101 or 121 or whatever you took. You want normally distributed data. Why? Because a lot of statistical procedures, such as regressions, t-tests, things like that, are based on the assumption that your data is normally distributed, is not terribly skewed or kurtote. And so this is a beautiful normally distributed distribution. Something like this is very skewed. Something like this is very kurtote. And so when you have data that is biased in a direction, it also reduces the wrong word. It either amplifies or de-amplifies variance, which affects error, which affects critical ratios, which affects your p-values. What I'm trying to say is the more non-normal your data is, the less likely you'll find significant coefficients. So you want fairly normal data. And if your data isn't normal, it also skew results so that you may have type 1 or type 2 errors where you find something that is significant that shouldn't be, or that should be significant that isn't. So we need to address normality. So let's go look at that. If we go up to we actually, check this out, we already exported this, but we'll do it a different way in a moment. But we already looked at skewness and kurtosis here in this table. Here's skewness and here's kurtosis. If we were to highlight these, here it is, conditional formatting, highlight cell rules greater than, the rules differ depending on who you cite. Again, that's common to most statistics. Most acceptable threshold, there isn't one. Most common practice, for skewness and kurtosis, again, there isn't one. Most rigorous, that'd be like the Shapiro-Wilks test, which I can show you. It's way too rigorous and almost nobody passes it. So I just like to use the most practical approach, which is about 3.8 actually, but that's not published anywhere, so I'll use 3. So if it's greater than 3 or less than -3, highlight cell rules if less than -3, then we have a problem. So let's go look here. Anything greater than or less than ±3. Actually, we're good. That's weird. Let's look at kurtosis. I'm just going to copy the formatting. If you go format painter, if you selected that, and then just paste it here, and it should have the same effect. Oh, I put on the wrong one. Dang it. So let's just do it like this. Conditional formatting, highlight cell rules, greater than 3. Okay, and less than 3, -3. We'll see if there's anyone violating our threshold. Well, this is problematic. Oh, yay, there's one. Okay. I was worried we wouldn't find any problems. So there are no problems with our Likert scales, which is great. That's a good problem to have. There's no problems. There is a problem with our age. It is highly kurtote. What does this mean? Well, let's go look at it. If we go to Analyze, Descriptives, Explore, Analyze, Descriptives, Explore, let's go put a few variables in here, including age. Let's do age and experience and frequency, how about? Just so you can see some normal and non-normal distributions. Put it in the dependent list, and in the plots, select a histogram. You can uncheck stem and leaf if you want. Okay, if you hit OK and hit OK, it's going to run these exploratory stats and produce plots. Here's age, highly kurtote, we'll talk about it. Here's experience, somewhat skewed. And here's frequency, fairly normal. You can see that box plot is tremendously normal. Let's go look at age. So here's the problem. This is kurtote. What is kurtote? It means there's very little variance. And when you don't have a lot of variance, you can't predict anything with it because it doesn't vary. It has to vary in order to predict. The way prediction works is you look at how one variable changes and then see how another variable changes at the same time. If they change together, then we're good. That change is variance. If there's no variance, there's no change. If there's no change, you can't do any prediction. So this one is highly kurtote. It looks like most of the participants were about 21 years old taking this survey. And the standard deviation is very small. And the youngest was 9. What? That's a problem. We should address that. We'll get to that in a moment. The oldest is 35. That's maybe believable. So context of your data, you need to understand your population. Our population in this case was sophomores at BYU. So 21 makes sense. Perfect. In fact, very little variance makes plenty of sense. We wouldn't expect a lot of variance in a class full of sophomores. So what do? Nothing. Except for that 9-year-old. We're going to do something with that 9-year-old. But in terms of the kurtoteness, we're like, well, they were the age they were. Like, there's not much you can do about that. And it also is rational. It's not like it doesn't make sense. If we had a bunch of 80-year-olds in this, it would make no sense at all. So you say, well, we had a kurtote age distribution, but it makes sense and is less than the Klein reference threshold, which is like 10 or something ridiculous. So we meet his threshold. We're good. But let's talk about this 10-year-old. Let's also talk real quick. What if we did have skewed or kurtote Likert scale indicators? Like what if one of these here was skewed or kurtote? Is there anything we can do about it? Can we like transform it or something? In a short ordinal scale that has like 5 points, transforming has 0 effect. It will do nothing except warp your data. So no, you don't want to transform a Likert scale. What if we had, let's say playfulness 4 was like a kurtosis value of 25, something ridiculous. we simply would delete that variable. It is too kurtote. Or if it had a skewness value of 25, it is too skewed. It will throw off the rest. And
would you mind repeating that last
yeah,
part?
yeah. So if we had a Likert scale item, like an ordinal variable that was too kurtote, too skewed, had a value of 25 or 70, I've seen some big ones. Since it is part of a reflective set of items that all ask the exact same thing, we are welcome to just delete that item. It's redundant for a reason. There's redundancy built in so that if you do have a problematic variable, you can delete it and it won't change what you're actually measuring. In other types of scales, let's say we had something like age or income, where there's only one variable measuring that thing. Deleting it is problematic, right? I mean, it's gone. There's no backup. And so you do everything you can to fix it. If you had something like income, where there's a huge range, or age, where it wasn't a kurtosis problem, but it was a skewness problem, and there was a lot of variance in that skewed distribution, you could transform them with a square root or something like that, or a log, and that would fix to some extent your normality issue. Anyone here work with raw data, like real, observed, like sensor data, things like that? Or is it all behavioral? Oh, all right, never mind. If you were to ever use like real data that has massive distributions, like from negative 1 million to positive 1 million, and you had skewness, there is this guy who invented YouTube, Gary Templeton, who invented, apparently he's a baseball player. Normality. Here it is, Gary. He's a good guy. He's out in Alabama or Louisiana or something. But he invented a two-step transformation approach right here that can normalize anything. Anything continuous.
I have used that several times,
yeah.
and I am totally flabbergasted.
It's amazing.
I don't understand how. And the beautiful thing about that transformation, and I checked this on several distributions, is that in almost every case, the mean and standard deviation of the untransformed distribution is the same as the transformed.
It's incredible.
Which means you don't even have to struggle in interpreting the coefficients.
Right. It stays on the same scale. So this guy's, it's amazing stuff. He and I actually just submitted a paper on this and its effects on real raw sensor data. It's cool stuff. So if you have data that's terribly skewed, look at his video, Gary Templeton, two-step transformation.
You said the data had to be continuous?
For something like this, yeah. Ordinal scales, when you transform them, because they only have a possibility of 5 or 7 or maybe 10 points, transforming them doesn't do anything because they're sort of fixed buckets it could be in. Whereas something continuous like age, income, sensor data that has such a large range, there are more gaps to fill in, more opportunities to transform. Okay. How are we doing? Do you guys need a quick break? Good. Yeah, let's do a 3-minute break. Now that Nancy's back. Yeah, let's do a 3-minute break. I know that means 5 minutes, but 3 minutes would be good. If anyone needs, bathrooms are that way, or the nice bathrooms are that way.
I just have a question.
Yeah.
My,
Remote folks will be right back.
when I'm exporting, I'm still getting this. I'm not getting the Excel file.
You're exporting the output, that's fine. So go back to the go back to this, and make sure you don't export this, but export the data. Yeah, I did the data. That's the data. So that export this. They're two different files. One is out for review of SD7. Yeah. Yeah.
So I missed this earlier, but you were able to change
Yeah.
But for me, area.
Oh, yeah. So go back to SPSS and go to edit.
beverage.
options.
We're gonna go look for vending.
I'm good right now, thank you.
And then
There are vending machines
is display names, and
downstairs.
also
Oh, you know, so actually,
names.
Okay, got it.
Yeah. Okay, that should do it. And then hit OK, it's gonna reset a bunch of stuff, but it should be good from here.
The criteria that you had for skew to kurtosis, because I know there are multiple formulas you can use.
There are a bunch, yeah.
To calculate them, and SPSS uses one, SAS uses the other one, all that stuff. So like,
Which one do you use?
which one do you? Well, I mean, they all kind of make sense. I mean, they're just different ways of looking at the. So for this, in this case, like, where did you get the 3 negative? 3.
So the 3, there is a publication on that, but it has been the most useful in practice for me. Anything above, honestly, it's above 3.8-ish, 4, tends to warp things and not play well with the others. And so I end up removing them anyway. Whereas anything less than about that, it tolerates everything else just fine and it works in the analyses. And if you were to like to remove it or not remove it, the analyses don't change.
Okay, cool. Yeah, that'd be really. Okay.
But there are citations for that. I think Hare mentions 3. There are others that mention 1 plus or minus 1, or the dividing the value by its error, which is really strict. Anyway, bunch of different routes.
Yes, yes. I always done it before with the median. I'd always, another stuff, that's the way I always, rather than just kind of looking at the neighboring value.
Yeah. And in the end, once you're changing 5 values, it's not going to be like a
I just need back.
if you've done some analyses already, you might redo them.
We don't have any.
Just age.
If you, we don't have age in our mind.
Oh, wait, yours, yeah.
That is here. So there's no
Yeah, the closest thing is frequency.
that's not an 8 or yeah.
So you're good at a lot. I'm here with you guys.
This is $100.
Such a good thing.
Amazon Prime. Amazon Prime, and it's USB 3. It's only your 3.0 ports. It's ours. It's a shooting next to power. I guess it's like a year and a half.
Working for that myself.
I love it. $100 on Amazon Prime. You get it tomorrow.
Such a good.
And, you don't have to go back and forth. I love them. I know Walmart sells one. Still is. I don't know if it's AOC. But they're slick.
These are one of our.
Especially for this stuff.
Never do it where yeah, there's like 10 of us here that you capstone words.
Yeah.
Second year.
And it's so weird when it comes with this little carry case. It comes with the carry case, cable, and the screen. 3 things.
Should be fine.
It's USB 3.0.
As long as it's office self-retirement, just take it out of the US. 5 months.
They're so nice.
As evidenced by, there's a couple people with that one.
But no, I had one of our assessors had last year. First a little bit nicer than this, but this is as good for, I mean, I'm not watching movies, I'm not super high definition, I'm not anything specialized, so.
Which is the drop anyhow. Which is drop the whole.
Dumb monitor. Dumb mixer monitor, that's. AOC, if you just type in,
That's like I did, you can just use the
AOC.
They're like $99.
When you read just the gas, you look around.
I think you guys are. I think you're working.
E60. EOC.
I think you are.
But that's it, it's $100, and it's.
So I got my first being able to transport something.
And it comes with the, I've had this for over a year, never had an issue. And you could, this one, the reason I like this one is you can do landscape portion, and it's just the right click. It's not super high def, and it's not touch, but it works.
Yeah, but so extension.
It's one thing. I don't know if they did last year. I didn't see the.
Well, we don't know that there wasn't. That doesn't say anything, right?
Oh, you're fine. No problem. All right, I think we're back. Yeah. Never mind. I'll show you. Let me show everyone. All right, we're gonna start up again. Just quick, during the break, someone asked, let's see, oh, hello? Oops, there we go. Yeah. During the break, someone asked how to pass this down all the way. Right, so let me zoom in. I wish my Excel zoom worked. Here we go. Okay. Okay, so someone asked how to fill all these rows. You should see, if I zoom in here, there's a little itty bitty tiny square right at the bottom right corner. If you double tap that, it will fill everything. But if you double tap anywhere else, aside from that like 1 pixel, it won't work. It's just that 1 pixel you got to double tap. Okay, you're welcome. Yeah. Or you can manually copy and paste, or type in the formula the whole way. That's no fun. Okay. We had a 9-year-old, right? That's a problem. We were looking at over here. We're back up and running. We had a 9-year-old here. That's problematic. It is highly unlikely that we actually had a 9-year-old here at BYU. The youngest I've ever seen at BYU is about 14. We do occasionally get 14-year-old prodigy kids, savants coming to BYU. Just weird. It's cool. But unlikely to have a 9-year-old. So let's go look at this 9-year-old. We can see in this box plot here who this is. It's record number 322. We also have a 35-year-old and a 34-year-old. But let's go look at record 322. Or we could just go over to age, which is right here, and sort it. Yeah, sort ascending. There we go, 9-year-old. This 9-year-old has 3 years of experience with Excel, which is cool. Been using it since she was 6. Not much other identifying information we can use. If we had like education in here, what?
It's 19.
Yeah, probably 19 years old is my guess. I wish we had kept education in here because I believe this case has 12 years of education, and she's 9, and so there's a problem there. My guess is they forgot the 1, so I'm just gonna type 19 there. Ooh, whoop, that didn't work. 9. Instead, if I had used the mean or median, what kind of difference would that make? Not a huge difference. This is 1 person. But the most likely value is the one I want to put in there. Okay, we also had a 35-year-old. Let's go sort descending. This 35-year-old, 5 years of experience, child order. Nothing here really gonna tell me whether this person's actually 35. Most likely, it's correct. Maybe it's 25, but we get 35s in our year-olds in our classes. I've had 50-year-olds in my classes at BYU. People come back for their education. It's totally reasonable. Yeah, go experienced students. Not a big deal. Why do we even care, though, is the question. And you've probably seen this from your stats, like intro courses. But if you have a relationship, let's see if this loads. Okay. If you have a relationship, this is Skew with a bunch of points. Let's say we have a bunch of data. on our XY relationship. And let me put a line of best fit in here. And let's say you have someone, let's say age is the x-axis, and Excel performance or whatever is on the y-axis. It's pretty linear. But let's say you have someone who says that they perform very poorly. Well, it changes that line pretty drastically to just that one point. Let me zoom out a little bit. Zoom out. If we were to put an outlier on the y-axis here, and that totally changes. There's no relationship now. It's a zero relationship. Let me let me move this one over to here. It changes things quite drastically. Now you say, but you said only 1 point's not going to make a difference. That's correct. When you only have, or when you have 300 respondents. In this case, we have like 8. And so every point makes a difference. But when you have 300, let's throw in a few more. Okay, we have quite a few more. Still very small sample size at this point. But if I throw in one up here again, look at that, nothing happened. Hardly anything at all. If I throw it down here, moderate change. So the more data you have, the less a single point is going to change things. But it does change things. So you do want to watch out for real abnormalities. Okay. Excuse me. We should look for outliers real quick on any of our non-ordinal data. So let's do a quick explore. Here's age, experience, frequency. Did we have any other non-ordinal? Gender. You can't have an outlier on gender. That's 2 points in this data set. Child order. That's it. So we actually did already. So let's go look at these other ones. The box plot will show you those outliers. In this case, for Excel use, no outliers. For experience, we have a few outliers. We have somebody who says they've used Excel for 15 years. That's a lot. We should go look at that. And then we looked at age already. But let's go look at experience. How long has Excel been in existence? Maybe 15 years? Because there was a version 1997, right? I think. Or 95 even. Wow, I'm getting old. Okay. Experience. I'm going to sort experience ascending. A lot of people have never used it. Let's sort of descending. Where to go? Sort descending. 15 years. We have 3 people who said they've used it for 15 years. These people are 21, 22, and 24. I mean, it's possible, right? My young students in here, when did you start using Excel? Like in school?
87 is, I Googled it.
87, wow.
And the Mac version came out even earlier.
Oh, like the Busy Calc or whatever it was. Yeah.
Just a couple years ago.
Just a couple years ago? Okay.
I used to know like 7th or 8th grade.
Okay. This is possible then.
6th is still a little younger than that.
Yeah. I mean, very unlikely a 6-year-old's using Excel. But I don't have compelling evidence to change this value. And I don't have a compelling need either. It's 1 point out of 300, almost 400. But you should be aware of it. What do you report? Nothing for this one. You don't report anything unless you change something. For the age we changed, you do need to report. Somebody reported they were 9 years old in my sophomore class. That's erroneous data. They meant 19. We changed it to the most likely value. Where do you put all of this sort of tangential, like peripheral information? I would not put it in the main body of your report. I would put this in a footnote or an appendix. This is not critical to your storyline, so it doesn't belong in the main flow of your paper. The only exception is maybe those who are doing the capstone, which we focus on that part of the paper. Okay. Influentials. I showed you influentials, adding a point, how that changes relationships. Let me show you it right now, another way to test it. In SPSS, if you go to Analyze, and I honestly can't remember what it's under. Cook's distance. Cook's distance. Analyze. It's probably under, oh, it's under regression, obviously. Go to regression, linear. So I went to Analyze, regression, linear. And let's stick in these averages I have down here at the bottom. I want to see if, actually I want to try age. Age is my independent variable. And I want to see if the extent to which you enjoy using Excel is predicted by age. But really what I'm doing is I want to see if there are any outliers in this relationship. Somebody, let's say I'll show you when we get there. How about that? Let's do, instead of plots, let's do statistics. I want to see, oh, it's in save, my bad. Save, Cook's distance right here. In save button, Cook's distance, this is going to show us how different every person is in this relationship. If I hit OK, we end up with our regression, which we haven't gotten to regression, but this regression essentially says, let me zoom in, that this sig is the p value, that age has no effect on whether you enjoy Excel. Here's age, dependent variable is enjoyment, p-value, non-significant, t-value, not critical. The actual coefficient, very small. But what I wanted to know was, is there anyone weird in this relationship? Let's say everybody, as your age increased, your enjoyment of Excel increased. And is there anyone who is total opposite, like their age was high and their enjoyment was low, something like that. And that's captured by the Cook's distance, which was recorded. When you hit save in any of these dialogues, it creates a new variable or set of variables. Here's the Cook's distance. I can now plot this if I want. If I go to graphs and chart builder, graphs, chart builder, then I can put, let's see, let's do a scatter plot, which is down here. 4 columns. And I can choose scatter plot. I think I have to drag it up there. There we go. Drag scatter plot up there. And I can put Cook's distance on the y-axis. And I can put just whatever. I can put age if I want, I guess. Age on the x-axis. What we want to see is there anyone who's like way out there? And here's someone who's way out there, but how way out there are we looking for? If you look on the left, you have the scale. It's a fairly small scale. Anything above a 1 is considered way out there. We don't have any Cook's distances above a 1. There are other thresholds that say, well, if there's anything that's an order of magnitude higher than the bulk, then it's an outlier. So the only one we'd really consider maybe as an outlier is this guy right here. And we could go check this person. They are the only 27-year-old in the data set, or 28-year-old, I guess, in the data set. So we could find out what their dealio is. But nothing to worry me here. If I saw Cook's distance that was greater than 1, I'd be a little concerned, and I'd have justification for removing them from the data set because they are far outside the normal of our population of interest in terms of this relationship. Okay, that's influentials. We talked about this. Yikes. Hope this isn't like a participant trying to call me. We talked about this. There are no outliers on an ordinal scale. We talked about that a little bit. On a 5-point scale of strongly disagree to strongly agree, it's hard to be an outlier. I mean, I can say I don't like something. I hate this company or something like that, and everybody else loves the company. I would be an outlier in that case, but I'm not an erroneous outlier. It's a true value, and so we can't get rid of it. It's true. The only case for getting rid of it is if people who hated the company were not within the scope of our study. So the way they answered is beyond the scope of what we're interested in. Then they're truly an outlier. Whereas the 9-year-old was truly an outlier. It was an erroneous response. We talked about this. Here are all the thresholds. Pick one. There are so many, and there are really strict ones, really practical ones, really loose ones. It's Klein, 2005, who says, 10. 10's a good number. Anything less than 10 is great. And so have I ever used that? Yes. I have had skewness values of 8 before. And I'm like, well, it's still less than what Klein said. And they've taken it. So there you have it. Okay, that's all the data screening we're going to do. Once you've done that, you now have a data set, a clean, usable data set that you can use for analyses, and you can be confident in the results of your analyses because your data is normally distributed. You've gotten rid of outliers and influentials, and you've gotten rid of unengaged responses. So anything you do find is likely to be a good representation of reality rather than biased or artificially inflated or something like that. So at this point, what I would do is I would save this data set as something else. I'd save it as like a clean data set or something like that. Clean. So I have the data ready. Anyone who would like that data set is now, it should be available on the Google Drive folder in the data set folder if you want to use this data set that I have right in front of me. Okay. Now, the next thing you need to do, this is outside of the stream of testing a theoretical model, but these are important pieces that you should understand. Significance testing. The whole point of doing statistics is to test some hypothesis, right? Or to fail to support some null hypothesis. And you can do this in different ways. You can do, you can say that two groups are different when it comes to something, like new employees versus old employees are different when it comes to performance, or when it comes to job satisfaction, or when it comes to autonomy. We can test this group and this group, their mean value for job satisfaction, and if those are different, hypothesis supported. And the way we do that is with a t-test if we only have 2 samples, 2 groups, or with an ANOVA if we have multiple samples. Also, there are different kinds of t-tests, ones that are like based on series of data. If I tested before training and after training, something like that, same population, before a test, after a test, before whatever, after whatever, then you use t-test. But if you have multiple, like more than 2 groups, you'd use an ANOVA. The statistic that they produce is roughly the same. It's just a critical ratio that says this is different from 0. This is different from nothing happening. I have an example here. Australians live longer than Canadians. That is a hypothesis. The way we test that is by taking the average age at death in years of Canadians, average year at death of Australians, seeing what those averages are and what the distributions are. And if those distributions are different, as shown here, then they are different. Hypothesis supported. If there is no significant difference, the critical ratio produced by it is not critical, then there is no difference. In this case, hard to tell just by looking at it. The mean for Canadians overlaps with the distribution of Australians. So hard to tell. We'd have to use a t-test or a ANOVA to figure that out. And we'll do that in just a sec. The other type of hypothesis testing is not differences in means. It's significance of movement, of correlations, of relationships. So we say that as autonomy increases, job satisfaction increases, right? They move together. This is a regression or correlation. You wouldn't test this with a t-test, although you could say low autonomy, high autonomy groups, and then test their mean job satisfaction, see if there's a difference. But again, you'd have to group that independent variable. So something like autonomy has an effect on job satisfaction. They move together. There's also what's called the null hypothesis, and it is a common practice error. There's a common error in practice to hypothesize the null. I get this a lot. I answer emails daily, a couple dozen every day from people all over the world. asking for statistics help. And one of the things I often get is, I'm testing that there is no effect between these two variables. And why would you do that? That is the null hypothesis, that there's nothing going on. That's not interesting at all. Unless all the literature out there says there's something going on and you believe there's not, then that's cool. In that case, the null is actually flipped. But you don't want to hypothesize the null. It is the default hypothesis. And the way you support a hypothesis is by rejecting the null, which is usually through a p-value less than 0.05 or something like that, which we will look at in a moment. Let's do this real quick. Let's do a t-test or an ANOVA. Let's do an ANOVA. I like those. Let's go to Analyze, Compare Means. You'll see t-test is here, multiple different kinds of t-tests, and then ANOVA. So I'm going to choose ANOVA. And these kind of compare means analyses are only good for testing hypotheses of differences between groups. So let's go down to the very bottom. Our factoring variable is the grouping variable. We want to see, are these two groups different? I have early adopters and late adopters. We could do that. Or we could do child order. Anyone here from a big family? Child order actually matters. I've come from a family of 7 kids. I was number 3. 10 kids. Child order matters. Middle child is awesome, right? Dang straight. Yeah, let's do child order. Okay. That's our factoring variable. So what it's going to do is it's going to compare whatever we stick in this dependent list across all different child order groups. And we can find out what those are in a minute. Let's see. How about enjoyment and decision quality? I want to know if middle children make better decisions than first child or only child or something like that. So I'll throw those in here. Options, I'm going to throw in a means plot. These are really helpful, especially when you have more than 2 groups. A means plot in the options. There are other things we can do, like a post hoc Bonferronis or Tukey's. These do pairwise comparisons between every single group. These are very useful. I'll throw one in just so you can see it. I'll do Bonferronis. They all do about the same thing. Most popular ones are Tukey's and Bonferronis. But it sort of depends on your field. Okay, if I hit OK, what this produces is several things. This box here is the overall model test. Says between these groups, when it comes to enjoyment of Excel, there is a difference. How do we know? The F is critical. The significance value, the p-value, is less than 0.05. There is a significant difference between first child, only child, middle child, last child, when it comes to enjoyment of Excel and when it comes to decision quality. But what are those differences? Well, if we come down here to the Bonferroni's test, it'll say, well, the only child is no different from the first of many. We can see that in the SIG column here. P-value of 1, absolutely no difference. But the only child is very different from the last of many. See the p-value here, 0. Totally significant. So it does pairwise comparisons. Let's go down here, though, to the means plots. These are easy to read. Here we go. When it comes to enjoyment, only child and first of many don't enjoy using Excel. Last of many enjoys it. Middle of many rocks it. And the quality of decisions follows a similar pattern. Only child and first of many, kind of low. Last of many makes better decisions. Middle of many makes best decisions with Excel. It's totally fabricated, by the way. I made up this variable because I'm a middle child. But the values are completely fabricated. The rest of the data is real. Just this is the only one that's not real. But you know, you gotta find vindication, validation. But that's how you'd run a test like this. Let's do a real one real quick with, instead of child order, let's do adoption, early adoption versus late adoption. It's this grouping variable here. Early adopter group. Hit OK. Same dependent variables. What this is early adopter is I'm a person who buys the very first version of the technology. I own 2 HoloLenses. I don't know if you know what those are. They're augmented reality headsets that don't sell to the public yet, really. I mean, it's for research only. I owned Google Glasses when they came out. I had the first Apple Watch. I'm early adopter. And then there's late adopters, those who purchase the technology after it's been totally vetted. I purchased iPhone 8. It's my first iPhone, that sort of thing. I wanted to see if it made it first. Anyway, so in terms of enjoying Excel use, early adopters enjoy it more. Is it significantly more? Well, here's enjoyment, p-value 0.073. Well, maybe. Depends on what kind of threshold you want to have. Some people say 95% is the only way to go. Others say 90%. Others say p-values don't matter. Look at the actual values. So let's do that. Actual values, not early adopters, 3.5. Early adopters, 3.6-ish. So not a huge difference in a 5-point scale. So is there really a difference? Probably not. When it comes to decision quality, there's bigger, nope, not a very big gap, 3.7 to 3.8. Early adopters make better decisions with Excel. It is significant at the 95% confidence level, p-value of 0.021. It's not that different. So what would you report? There's a significant difference. Hypothesis supported. Limitation. That difference was nominal. Okay.
James, could you go back and just state that hypothesis again?
Yeah, so the hypothesis here would be, this is early and late adopters. It would be something like early adopters make better decisions with Excel than late adopters. Yeah. Or early adopters enjoy using Excel more than late adopters. Yeah.
It's kind of a very silly question. I'm playing here with your data, and when I try to run the ANOVA, it shows the labels instead of the number.
It's showing the label, the whole question.
How do I change that?
Yeah. So back to that. Whoops. Here we go. For those who are still seeing labels in here, like big words instead of just the names, you go to Edit. This is slow. There we go. Edit, Options. And then in the General tab, make sure you have Variable List, Display Names. And in the Output tab, make sure these two boxes here say Names and then Labels, Names and then Labels. Most people will start, the default is labels, 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 labels. So change those to name, label, and then hit OK and it'll change everything. Okay. Okay. We talked about variables moving together. We talked about this already. As one moves up or down, the other moves in another direction. If it's synchronous in the same direction, then it's a positive relationship. Even if they both move down together, it's still a positive relationship because they're moving together. If they move opposite to each other, like this, that's an opposite. That's just a weak positive relationship there. But if they move opposite, like this, there we go. They are moving at the same time. They are moving synchronously, just oppositely. And so it's just a negative relationship. I get this question a lot, more than I should. Dr. Gaskin, my coefficient is negative. Is there an error? No, it's just an inverse relationship. As one goes up, the other goes down. That's perfectly natural, unless it's not. Like,
Is this the example you gave us in class with the balls?
So that's a different one.
Okay.
Yeah, we'll cover that in factor analysis. Okay. Yeah. So as variables move, this is one of my favorite slides. I could watch it all day. As variables move, they create variance, right? Those distributions have variance, but some of the variance is attributed to the actual trait we're trying to capture. So let's take autonomy, for example, perceived autonomy. We ask you, to what extent do you feel you're in control of setting your own work hours, setting your own tasks, performing your work at your discretion, things like that, autonomy. And you answer the way you feel that autonomy. But only a piece of the way you answer is attributable to the actual way you feel. That's the trait, the thing we want to capture. There's also some that is error, that you weren't able to respond accurately for some reason. Maybe I gave you a 3-point scale and you're like, well, I'm not a 2, but I'm not a 3. I'm like a 2.5, right? That's a problem. It's input error. You can't get an accurate value. And if I gave you a 100-point scale, you're like, I don't know. I'm somewhere between a 60 and an 80, somewhere. So you just put 70, but that's not the true value, right? That's some error involved there. And maybe someone else will feel the same way, but they'll put 80. They'll put 80 because they're feeling good that day. There's also response bias. Oh, I just talked about response bias. My bad. Response bias is error in the way you capture it. This could also be influenced by the way you think the question should be answered. Those questions about gossiping and things like that. Of course I don't gossip. Of course I don't get even. And so you answer it the way you think it should be answered. That's response bias. Or let's say you're at a company that you love and you just love your company so much. And then there are questions about how well is your company performing. You're more likely to answer that they're awesome, they're doing great, they're an innovative company, they do innovative things, because you have loyalty to that company. And so the true value may not be being captured accurately. So there's response error. Sorry, this error, I should call this measurement error. I'm going to do that right now. Measure. Or not. Oh, there we go. Measurement. Boy, it is really slow. This measurement error is error in a calculation. I'll show you in a relationship. That is responding very slowly. One moment. My computer is just like sluggish. Here we go. Okay. So this is error in a relationship, and I'll show you that down here. If it responds, my goodness. In this relationship here, you see we have error. We have the error is between the actual response and the line of least error, the line of optimal fit. That is that error we're talking about in the variance, is the extent to which it doesn't match everyone else, that error. And anything you predict has error, because anything you predict has an optimal response, and your distance from that optimal response is your error. So there are different types of error we're getting when we capture this, when we capture data. And the only one we want to predict is this trait. So that's good to bear in mind. There's a lot that goes into the variance of a measure. Okay. This is just for fun. Finding a significant coefficient doesn't always mean that it's meaningful. This is the correlation between total revenue generated by arcades and computer science doctorates. Actually, this one might be real. That's a bad example. There are some that are less, more spurious, like the amount of cottage cheese eaten in Alabama and the number of strangulation deaths in Louisiana. There might be, dang it, number of Nicolas Cage movies and debt or something like GDP. Yeah, so there's some weird stuff.
No, I think there's a causation there.
Dang it.
Nicolas Cage movies and drownings.
We'll find it. There are spurious correlations. That's what I'm trying to say. So make sure your significant p-values are backed up. In fact, there are journals now that won't accept papers that just report p-values. They say this is not enough. You need to go collect qualitative evidence that your p-values are meaningful. Yeah. So the last paper I submitted, we actually did an experiment with treatments and controls. We went and surveyed hundreds of people, and we collected interview data from experts and professionals. And all three of those things combined support the p-values we found. It's a lot of work. Okay. Linear regression we talked about. regression's not that complicated. There's the formula for it. You're trying to predict y. You have known values for x. Oops. And some amount of error, right, between what you said and what the optimal answer is, which is essentially the average of everyone else's based on these two variables. So that's regression, and there's some intercept. Not that complicated. You can do some cool stuff with this, though. Just finished a project in Georgia. We needed to predict using archival data with lots of X's and one Y. Our Y was, will veterans with disabilities have a job, a stable job, after 90 days of counseling? 90 days after counseling, not 90 days of counseling. Anyway, we had tons of data, tons of X's, gender, education, type of disability, severity of disability, and 37 different predictors, different X's, and we had to predict Y. And we were able to very accurately. And so that the next time they have a veteran come into their office, they can ask them all these questions and then be able to predict with precision the likelihood of that person having a job after 90 days. And if not, if it's a low value, what they can do to make that prediction value increase. It's a pretty cool study, but it used the massively complicated linear regression equation. I mean, that was it. They paid us to use linear regression. It's awesome.
How many people were in the study?
53,000 was our sample size. Yeah.
Great.
Yeah, it was great. So we had a lot of precision because we had very little sampling error because we had the entire population, not just a portion of that population. Anyway, cool study. But again, I get asked now and then to do these consulting jobs that are like big jobs, but they boil down to a t-test or an ANOVA or a regression. Like, that's it. I got to make it look like it was awesome and hard. And I slaved over this for weeks, and I earned that money, right? I mean, I earned that fee, but it was just a regression. It was a complex regression. It was just a regression. Okay, anyway, what I'm trying to say is you're getting powerful by learning this. So much power. We've talked a little bit about confidence in findings. You want to be confident. How confident? 95% confident is typical for psychology-based fields. Anything in business, aside from accounting and finance, is psychology-based. Anything in the humanities, psychology-based. So 95% is pretty good for social sciences. In physics, they prefer far more confident. You want to be absolutely certain, 1 in a trillion, 1 in a billion, that you're not wrong before you say, we found something. So know your field. I've actually gotten away with 90% confidence in some studies. I said this is exploratory, so we're more willing to have a lower confidence level. Let's talk real quick about this, and we'll go back to the previous slide. So in statistics, there is a common error in practice. We're getting better about it, but there is a practice to just say, here's my hypothesis, here's the p-value, hypothesis supported, right? Or hypothesis not supported. But the p-value is what we call a local test. It is the last thing you use to support your hypothesis test. First, you got to see, is your data even valid for running your analysis, which we did at the very beginning. We screened it, got rid of outliers, unengaged people, and now it's valid. Well, once it's valid, well, then you got to test whether your constructs, we'll call them factors in this case, whether your factors are even valid. If they're measuring what you think they should be measuring. We're going to talk about that more this afternoon and tomorrow. And if they're not valid, well, then ignore the rest of this stuff lower, these local tests. Then once you do that, is your model even valid? So you have valid factors, but is the way you're relating those factors to each other even a valid formation of relationships? If not, then R square and effect size and p-value don't matter. Let's say it is a valid model. Are R squares substantial? R square is, let me go up to the previous slide, R-square is the extent to which you can predict some dependent variable. In this case, 42%. We can predict 42% of monthly sales using these two variables, attractiveness and confidence. This is totally made up data. But 42% is a good number. I mean, that's significant. That's meaningful. Let's say this was 2%. I've seen that in published papers. 2%. Who cares? But my p-value is significant. Who cares? It hasn't met that global test of meaningfulness. And so your significant p-value is meaningless. Then effect size, that's sort of the extent to which the relationship you're talking about, the hypothesis you're testing, has a bearing on the model itself. So for example, in this previous relationship, let's say that attractiveness is what it's all about in sales performance, right? And confidence just happens to be a happy byproduct of attractiveness. If I were to remove confidence from this relationship and the R-squared changed by like 0.02, the effect size is very small. And so even though it does have a significant effect, the p-value is significant, its effect, its actual coefficient effect is very small and meaningless. And then finally, after we've demonstrated all that global stuff, then we can get local and say, and check it out, the p-value is significant, therefore. But unless you go through this whole process and validate all these global tests, then your local tests are meaningless. So as you're reviewing papers and as you're writing your own papers, watch out for that. You'll see people just report p-values. Not good enough. Got to do more. We talked about that.
I have a question.
Yeah.
So that model that you showed,
yeah,
does that whole thing even work with very simple experiments and data?
Oh yeah. So let's say we're not doing some complex SEM model, structural equation modeling. Let's say we're doing something like something with two observed variables, something like years on the job and income, right? Something very simple. Data validity still counts, right? You gotta have valid measures. Factor validity doesn't count because they're not latent. It's only a single item per idea. So factor validity doesn't matter in this case. Model fit doesn't matter because you only have 1 degree of freedom. Actually 0 at that point. You have 0 degrees of freedom in that model. R-squared does matter. If years on the job only predicts 1% of income variance, then meh. Effect size again matters and p-value matters. Yeah. But especially with SEM, this is very important.
So we just kind of review because I was probably taking notes.
You're good.
When you give the example of the effect size for confidence, right?
Yeah.
So basically, we're saying that if you predict that if confidence only affects, taking confidence out.
Yeah, taking confidence out only removes, only drops the R-squared to 40 instead of 42. Well, then obviously confidence isn't having a lot of bearing on the model. Confidence isn't the main predictor here. And even though we have a significant p-value, if we were to remove confidence, would we be losing anything? That's what effect size is talking about. Are we losing anything by removing it?
So in that case, we just remove confidence.
You could, yeah, you could. Although in this case, it's part of my theory, so I want to keep it.
Oh.
And then the limitation is what I would report. I'd say, but the effect size is really small. Yeah, that'd be in my limitations section. Yeah.
Another question. So let's say that you're doing a multiple regression.
Yeah.
And you have your 32 predictors.
Yeah.
Then now that you have a lot of degrees, like more degrees of freedom, how would you test your model fit?
In that case, if you only have one dependent variable, still there's 0 degrees of freedom. If you have multiple dependent variables and not all of them are predicting both, and there's no relationship between the dependent variables, then you do increase your degrees of freedom, and so model fit does matter. In this case, you could only test model fit through, is that what you're asking? How do you test model fit in this case?
Yeah.
What you would do in SPSS or some other first generation type software that doesn't do SEM is you would check if adding a path that wasn't naturally there changes the R-square. If it does, then you should have that path in there. Otherwise, your model doesn't fit. There are also thresholds for this. There are metrics for it, the AIC and BIC, which you want to minimize. And if you add that path and it drops your AIC quite a lot, then your model fit was poor before. So you know to change it. Yeah. In SEM, it's way easier. It produces a whole set of metrics for model fit. And, yeah, we'll talk about model fit more Saturday. Sweet. Yeah. Okay. I think we're getting down to the end of these slides. I'm so excited. For lunch. So excited. We talked about this a little bit. The relationship between certain measures. So your sample size, we've talked about sample size, and having a small sample size introduces a lot of error, right? Because you only have a few points to draw on. If we go back to this here, when we had only a few points, a low sample size, every point made a big difference. And every point created more error for everyone else, right? Well, not really. It actually reduces error for everyone else, but every point moved that line a lot. The more points you add, the less this line moves as you add more points. So error is being minimized. The more sample size you have, the less error, which means more power. So sample size goes up, error decreases because you have more to work with. It's like if I were to sample just these three people on how hungry they were, or no, sorry, I'm thinking about lunch, on how much they're learning, I may get a skewed, error-filled response. Whereas if I sampled this portion, exclude you guys, the average I get from your level of learning is going to be very similar as if I were to add these. The error wouldn't, the average wouldn't change much because error was minimized. Whereas if I sample these guys and then checked you guys, there might be totally different averages because it's small sample size. So the more your sample size, the more you decrease error, which means if you decrease error, your confidence goes up and your critical ratio goes up. Critical ratio is like a T statistic, an F statistic, in some cases a Z. And these are the tests of amplitude, the size of the impact of the coefficient. And the further it is from zero, the better. The closer it is to zero, the more likely there is nothing going on. The less error you have, the higher that value is going to be. And the higher that value is going to be, the lower your p-values are going to be. Because the p-value is actually calculated directly off of a critical ratio. You remember those tables from statistics classes? You got to go look up the table value in those big matrices. So you're looking up the critical value in that table to find the p-value correlated with that critical value. Anyway, so that's how those all relate. So the point here is more sample size is usually better. 53,000 for that study we did gave us tremendous confidence. We knew exactly what we were getting. And if we were to add 5 more or 30 more veterans to that sample, it would not change our results at all. In fact, what we ended up doing was we split the sample into 26,000, 26,000, and ran the two models completely separately and ended up with exactly the same results, down to tens, hundreds, thousands, down to a 1/1000th on the coefficient. Even though they were two totally different data sets, we just reduced error so much by getting so much data that it was very consistent, very reliable. Yeah.
So what happens in like an ANOVA where you're taking your information and you're dividing it into smaller groups?
Yeah.
Are you introducing more error?
So the question for those who couldn't hear remotely, what if you have multiple groups, like in ANOVA or later on a multi-group analysis? Every group is considered a separate sample. And so every sample would have to meet sufficient sample size requirements. So let's say we're testing men and women, and we only had 30 women, and we had 80 men. Our limiting sample size is 30, not 80, or not like halfway in between. It's the smallest sample size that limits us. This actually becomes a problem when you're doing anything in the technical field, if you're sampling or leadership, which is a problem, right? You sample leaders or sample programmers, you're going to get a male biased, at least in the US, I don't know about elsewhere, but you're going to get a male biased sample. And if you're going to make any comparisons between those two groups, you're limited by the smallest group, not the like average of the size of the groups. Oh. This is really important stuff. It may seem super simple. This is so important to understand because these are the levers by which you can have higher reliability.
James.
Yeah.
If the population is indicative of males,
yeah,
would it then be?
Then it's not biased, right? So the question was, if the population is actually more male than female, then it wouldn't be biased. It would be representative.
Policing law.
Yeah, law enforcement, same issue. Yep. Firefighting. Yep. Okay. Oh, we finished. Yeah. Cool. Okay. So, I'm so excited. We finished everything. That I was planning to finish this morning. These are exercises. If you don't have your other things you have in mind to do during lunch, if you wanted to practice these things, here are my recommended things to practice with your own data if you have it, or with mine if you don't. These would solidify sort of what we talked about today. But I would we have 20 minutes. There's some other things I can show you, which would be useful, or I can spend some one-on-one time with you if that would be more useful. There will be time for one-on-one, hopefully tomorrow during lunch or Saturday, maybe even after sessions here and there. So does anyone have like strong, passionate response? Please do this one. Or should I just pick something?
ANOVA.
ANOVA. So we did in Excel or in SPSS? So you can do everything like regression, ANOVA, and correlation in Excel, which is useful for those who don't have SPSS. I can show you that. We did ANOVA in SPSS with child order, and yeah.
So R squared.
Sorry.
R squared we didn't talk about.
Free software that the name is JASP.
JASP?
Yeah, and it's really close to SPSS.
Oh,
so
cool. I've never used it.
Need, the Excel version.
Not even Excel. Cool. I've never tried JASP.
It gets you the size effect and a lot of T of Welch and something.
Cool.
I'm biased in statistics, so.
Okay, JASP. I'll take a look.
Yep, and it's got a Mac version too.
Nice. Mac version. Cool.
Thank you.
Yeah, man. Yeah.
Can you show us how to do these in Excel?
Yeah, I can show you in Excel how to do these. Check it out. So if we had our data in Excel, which we do right here, I'm trying to think if there would be a better way to, real quick, let me check this, and then we'll go to it. If your model does not call for using age as a control or another type of variable, does it matter that there's a statistical outlier of 9? Good question. Yeah, if you have an outlier or weird stuff on a variable that you're not going to use, you don't care. You're not going to use it. So it doesn't matter. You don't have to fix it. Okay.
But what about the other rest of the data?
But the data that you are going to use, you better fix it.
So what I'm saying, if the age is not part of what you need, but what about the other information that
Yeah. Yeah. So you'll want to check all their other responses and make sure they're valid. Yeah. Good. Let's do this. I want to show you some data that's a little bit more tailored for this already. Stats. Where did I put it? Oh, I know where it is. This will be a watch with me instead of do with me for a moment. I have some data that's already prepped for ANOVA, t-test, correlations, things like that. Here we go. And stats. There we go. So you don't have this, I'll just stick it in the folder. Why not? Let me stick it in the folder we have together. It is now in the folder if you want it. It's called Stats Practice New. And it's data that's a little more prepped for these types of analyses. It's opening. Thinking. My computer's running so slow. I think it's because I'm recording the session. It's getting long, and so it's filling up memory. So here we go. All right, here we go. So if you open this up, oops, control function page down, page up. There we go. Now there should be several tabs. Man, my computer's really hurting. What's going on? Let me close some stuff. Okay, well, back to Excel. What you can do is, let's do correlation first. That's easy. On the correlation tab, what you have to do is you have to get the stats package. If you go to the go to the data tab up top. If you have the stats package, here's the data tab. If you have the stats package, it'll show over here as the data analysis. But most of you probably won't have that already. So the way you get that for free, you just go here to File, and then go to Options, and then it opens up this dialog box. You want to go click on Customize Ribbon. And then if you want to be a jerk, uncheck all these boxes. You can literally take off all the tabs in the ribbon. Don't do that. But you could take off like the home tab for your buddy, and it would be gone. He'd be like, wait, where's the home tab? How do I copy? You can take off all the tabs. You can do this in any Microsoft product, by the way, if you want to do a prank. Anyway, don't do that. Sorry, that was not what I was trying to talk about. Go to, sorry, it wasn't ribbon, it's add-ins. I got distracted. Go to add-ins. And then down at the bottom, you'll see Excel add-ins and hit go. And then that'll open up this, and then make sure analysis toolpack is checked. You don't need the solver one, that's for something else. But analysis toolpack, make sure that's checked. Once you hit OK, it'll show up here in the data and analysis. If it doesn't, just restart Excel and it'll show up. But once you have that, click on it. And then you have all sorts of options. Check this out. You have ANOVA, correlation, descriptive statistics, F-tests, histograms, all sorts of stuff. So I'll do an ANOVA real quick. Not a two-factor. Let's do a single factor. Not ANOVA. I was going to do correlation. Sorry. Correlation. Hit OK. It says input range. Well, I just want all my variables here. How about all of these? Selected all those. My labels are in the first row. And I want to output this to a specific location. I would just right here, right there. And then hit OK or create. Here it is OK. And it thinks for a sec and produces, zoom out, correlation table. Here it is. And this is the extent to which every variable is related to every other variable. You can reduce the number of decimals if you want over here in the home tab. It's this back decimal button here. That's all right, I have some ones up there. That's my error sound. Stop error sounding. Oh, it's because I have non-numbers in there. My bad. Okay, anyway, and my computer's running so slow. I don't know what is causing it to go so slow. This is crazy. Anyway, so that's correlation. You can also do a correlation. Check this out. You can do, if you just want two variables, do equals correl, and give it two arrays, two columns here. So let's do how is life satisfaction correlated with, comma, with brushing teeth? How about that? And the answer is, it has a 0.3 correlation. Brushing teeth and life satisfaction makes you happy. The more you brush your teeth, the happier you are. Again, fabricated data. If we're a negative relationship, I think there is one actually. If I go to, let me go up here. Oh man, it's slow. Okay. If I go to equals, my goodness, it's killing me. Equals correl of eating vegetables and having friends. Yep, negative relationship. The more you respect eating vegetables, the less friends you have. Okay. Again, fabricated data. If we were to do regression, same idea. Let's go to the regression tab, and if you go to data, data analysis, go find regression down here. There's regression right there. You have Y is what you're trying to predict. So in this case, let's try to predict life satisfaction. And X is the thing I'm using to predict it. I can select one or many columns. I'll go ahead and select all of these columns. And my labels are in the first row. My output, I just want my output to be right here. And hit OK. It says no good. I probably shouldn't give it the whole column. I'll give it just what's relevant here. And then over here, give it just what's relevant. I was selecting the whole column down to like row million. So it's probably the error it was giving me. There we go. And scroll up. Here's all the output, including the R square. Let's see if it'll let me decrease decimals. No. Okay. So here's the R square. I'll just zoom in. Pretty good R square. We're able to predict life satisfaction really well with these variables. Here's the significance value. It is very small. That's a scientific notation there, but it's 0 essentially. And then if we want to know for every variable separately, here are all the coefficients over here on the left, right here, and the p-values right over here. So we can find out which ones actually have an effect. It looks like eating your veggies has an effect on life satisfaction, a negative effect. That's interesting. And having friends has a positive effect on life satisfaction. Oh, and then sleeping well has a positive effect. Cool. Again, made up data, but you see how it works. And the last one would be ANOVA. Here's ANOVA.
So sorry, while we're on
Yeah.
that, James, so if you found a very low R squared
Yeah.
between two things, you would
Even if,
report that, or-
yeah, if the R square is really low, like 0.02 or something like that, and I still find a significant p-value, I'd report that the test was supported, but limitation, it was a very small effect. So take it with caution. Yeah. ANOVA, same idea, data analysis. Let's go up to ANOVA, single factor in this case. Input range is just the variables I want to see. Let me explain this data. This data is life satisfaction values. That's what all the numbers represent of these different groups. So there's a young group. This is the old group. That can't be right because I have life satisfaction in here by itself. Anyway, ignore that column. That's what this is supposed to be. Oh, no, this is just old and young. Okay, my bad. This is the actual values for having friends, life satisfaction, watching TV between old and young people. So is there a difference between the old and the young when it comes to how many friends I have or how important I find friends are, whether I brush my teeth? Let's do brush teeth. I bet there'll be a difference there. The amount of value I place on brushing teeth. Labels in first row, output range here. And there it is. The answer is p-value right here in scientific notation. Just make it normal number. It is 0. The p-value is very low. If I were to look at old versus young, the average value, old people tend to attribute more value to eating their vegetables than young people. And there's a significant difference. So that's ANOVA in Excel. Cool. You can do a bunch of other things in Excel too. A bunch of statistics. There's actually there was a big initiative a few years back, like 10 years back. Excel was producing a full statistics package, like a program. It's called Excel Stat. And they brought on a bunch of major statisticians to get it right. I don't know if it ever turned out or if they're only selling it to enterprise, but it never really came to the frontline consumer. Okay. Anything else up there you really, really, really want to see?
Logistic regression.
Yeah, logistic regression. So we've done linear regression, which is when you have independent and dependent variables that are numerically meaningful. As the value of the variable increases, so does the value of the trait. So for example, job satisfaction, a 1 in job satisfaction is low job satisfaction, a 5 is high job satisfaction. Whereas logistic regression doesn't require that constraint. It can predict or use as predictors categorical variables, such as marital status. A 1 in marital status is not less marital status than a 5 in marital status. It's just a different status. Like 1 would be single, 5 would be widowed or something like that. Totally different. And so you can predict you can predict membership or likelihood of that dependent variable value using logistic regression. The way you do that in SPSS is in analyze, regression. There are different options for logistic, binary and multinomial. Binary, obviously, when you have a binary dependent variable, such as gender. Multinomial, when you have multiple value category, such as religion, marital status, child order, things like that. Let's just do a binary for ease of interpretation. Hello? Man, my computer's not liking this. There we go. So our dependent variable in this case needs to be a binary variable. So I'm going to choose gender. There's gender. And then my covariates can be either either categorical or continuous or ordinal, excuse me. So let's say I can predict your gender based on age, experience, and frequency, something like that. And if I had categorical variables in here, I'd want to specify that they were categorical, but none of these are. I hit OK. What comes out, it looks a little bit like a regression, but it has to be interpreted differently than a regular regression. So I'm going to go straight down here to this variables in the equation table. And I'm going to copy this out so we can zoom in a bit. Fine, I'll zoom in here. Okay. Here we go. So what we have here, I should do it down here. I keep wanting to point at the screen, but nobody remotely can see me when I point at the screen. I'll do it with my mouse. Okay. What we have here is the predictors of gender. Age, does it predict gender significantly? It does. Look at that, p-value 000. And the way we've coded gender is male is 1, female is 2. And at BYU, the data is funny. Males tend to defer college for 2 years, while females do not. Females go straight to college, and males tend to go on missions. They go for 2 years to go teach the gospel to people all over the world. I went to Malaysia. And then I started my freshman year at BYU when I was 23. So what this is saying is, because it's a negative coefficient, it says that as age increases, you're more likely to be male, the lower end of the binary scale, because it's a negative coefficient. If this were a positive coefficient, this would mean you're more likely to be female as your age increases at BYU. Experience, no effect. Frequency, there is an effect. Now, since, again, binary outcome variable, negative coefficient, it means as the frequency of use increases, you're more likely to be male than female. You're more likely to be the bottom end of the binary scale, negative coefficient. Positive coefficient means higher end of the scale. That's weird, right? You have to interpret binary outcome coefficients a little differently.
Yeah. Is there any way at all to graph any of these things?
Oh yeah, you could totally graph that. The easier way to graph this in this simple way would be to do a t-test or ANOVA and just show the mean differences. And to not do a logistic regression. You could support your logistic regression with an ANOVA, which is essentially what it's doing anyway. It's a slightly different algorithm, but same outcome. That's logistic regression. Anytime you do logistic regression or have a categorical outcome variable, there is a reference category. It is the 0 or the non-represented value. In the case of gender, where male is 0 or 1 or something like that, and female is 1 or 2, the higher end of the scale, this gender variable is actually not gender, it's female. We're predicting femaleness. Does that make sense? Yeah, because it's the higher end of the binary scale. So if we have a negative coefficient, you're less likely to be female, i.e. you're more likely to be male. Logistic regression is a little tricky, but it's just you're got to interpret your coefficients in relation to the reference category. Okay, it is noon-ish. Anyone remotely have anything before we go? And then we'll get back together in 2 hours. Anyone remote need anything?
Okay. James, that Google Drive link didn't arrive yet. Type from Ireland.
Oh, it did not arrive?
That's right, yeah.
Okay, email. I put it in the chat area, actually. If you go here to chat, it's up. It should be the first chat to you. Do you see the chat area?
Not really, no.
So in Zoom, there's like a toolbar somewhere, and there'll be a chat area. You'll need to find that.
Okay.
Cool. And the links.
I'll try that, thank you.
Cool. All right, see you guys in 2 hours.
Jake, can we leave the stuff in here?
Yeah, you guys can leave your stuff in here. Is anyone staying in here the whole time? Okay, what I can do, I can go get a key and we can lock this. It's BYU. Probably be fine. But if you want, you can put your stuff up in my office. We could do that if you feel more comfortable. Okay, I'm going to stop recording.